Hello, here we'll be presenting the deployment procedure and outcome of this microservice application, which is built on top of the MERN stack, Mongo, Express, React, and Node.js framework. We can see this architecture diagram of the microservice application with which we are going to work. The application consists of 4 custom application microservices, which are the post service, comment service, query service, and the front-end service, and 2 third-party supporting services, which are RabbitMQ and MongoDB. These independent services together will function as the microservice application. We'll try to discuss these services, how they communicate between each other and communicate with the outer world through the internet. For example, with the browser through the internet. And if I talk about the feature of this microservice application, it can be scaled with the Kubernetes deployment in the cloud, which means the Kubernetes cluster in the cloud will help to increase the resources of this application based on the configuration and the applied load on it. And each service here, the post service, the comment service, or the RabbitMQ or MongoDB service, here is independent, which means if one service is down, it won't make the other services down. They will be functioning independently. And for this reason, these microservices are scalable and independent, which makes this application reliable. Now, how this microservice application is reliable, we'll try to discuss this practically and all about the communication stuff later, once we will have our app deployed on the cloud. We can see we do already have the microservices and application code built. Here we do have 3 backends: post service, comment service, and the query service, and also have the front-end service. And then we do have all the Kubernetes configurations here and the Terraform configurations here to deploy the microservices on the cloud. It's going to be more about the automatic deployment of the microservices in the cloud and configuring the things based on that compared with the application and its functions. So now let's talk about what we are going to do to make these microservices functioning with the AWS cloud. We will first create necessary accounts in the AWS cloud. Then we will configure GitLab to automate the deployment on AWS cloud before we push the code at there. Then we will run necessary Python scripts to create and configure some networking resources into the cloud, which are the prerequisite before we create the Kubernetes cluster and deploy the application. Then finally, we will push the code and trigger the CI pipeline for the automatic deployment of the application. And after that, we will be performing some manual tasks to expose our application to the internet, and then we'll be validating the created resources and testing the application from the cloud. And then lastly, after finishing the test of the microservices and the application, we will be performing the deletion task to remove all the resources which will have there on the AWS cloud, so that it doesn't cut any unnecessary cost for us, as this deployment is only for describing the microservices and testing the things for the application. Let's start with our first task, which is creating an AWS account. We can create an AWS account or root user account from the AWS Management Console. Let's see how we can create one. Search AWS in the browser and then go to the first link. It will land on the AWS Management Console page. From here we can create an AWS account. To do so, click on the create an AWS account or create a free account. Both options are same here. We can see here what they offers in their free tier. Amazon EC2 up to 750 hours for T2 and T3 micro instances. Amazon S3 up to 5 GB of storage. Amazon here DynamoDB up to 25 GB of storage. Actually, this free tier is not going to be helpful for us, because here we can see some of the services offer free tier with specific optional limitations, and the resources which we are going to create are different from these options. So for our deployment, it's going to cut almost 10 to 15 USD per day if we can manage the resources properly. So let's go with create a free account. Then provide the email address for the root user and the account name, and then verify the email address. And after that, we will have an AWS root user account with which we will be able to perform any operational task within the AWS cloud. But to create the resources and deploy application, it's suggested to work with an IAM user account, but not with the root user account, because developers get IAM user account from the project owner within the company for which they work for. So it's a best practice to do so. Now let's quickly create the IAM user account. And to do so, we will go to the console home and we will sign in as the root user. This is our root user email address. Click on next, then password auto selected, sign in. Then we'll provide the MFA code from our authenticator app. Submit. We have successfully signed in to our root user account. Now to create the IAM user account, we'll go to IAM, then users, then see we do have already one IAM user account created. I have created this one 97 days ago. Now let's create another, create user, then let's name it 2, and then let's check this one, provide user access to the AWS management console. If we check this one, we'll be able to perform the management task with the resources from here within the console also, and also from the terminal. So let's next. Before click on the next, I want to create IAM user, and then let's select the custom password, and then let's provide a password for this. Now let's uncheck this one. Users must create a new password at next sign in. This will require time, so we have unchecked this one. Now let's click on next, and then let's select this one, attach policies directly. Now let's first select this one, administrator access, and we'll select another one for billing. So let's click on next. So these are the two permissions which have been provided to the IAM user. Now let's click on create user. So the user account, IAM user account, has been successfully created. Here we can see the console sign-in details, and this is the URL using which we can sign in to our created IAM user account. This is the username and password, and we can download a .csv file which will include the sign-in credentials for the IAM user. From here we can see it includes the username, password, and console sign-in URL. So using this info, we can sign in to our created IAM user account. So before we do sign in to that account, let's enable the billing access for our IAM user account from this root user. So to do that, we will select our account name, then we'll go to account, and then from here let's scroll down until we find IAM user role access to billing information. So make sure this is activated, which ensures the access to the billing information for all the IAM user account which are going to be created in here using this root user account. Now we can go for signing into our IAM user account to work further with the AWS and our project. We saw previously that we do have our microservice application code built, and we do have that project inside of the GitLab already. Here we can see we can create new project or work with the existing one and then configure for the CI/CD to automate the deployment process. The configuring process is going to be the same. So let's see how we can configure. First, to enable the GitLab instance runners, let's navigate to the project. We do have already navigated here, and then settings, CI/CD. In here, runners. In here, turn on the gear icon to enable the instance runners for this project. We have done it already, and ensure at least 200 unit compute minutes are remaining to run the pipeline with these GitLab owned instance runners. It can be ensured from profile, then preference, then usage quotas. Here, from here you can see we do have almost a total of 1000 unit compute minutes. For every month, one free account will have 400 unit compute minutes for the instance runners from GitLab, which is sufficient to test this project. To explore more, need to buy compute minutes. A 1000 unit compute minutes pack can be bought with 10 USD. To buy, we can click on here, buy additional compute minutes, then follow the instructions. First sign in gitlab.com and then follow the instructions. Let's sign in, and then from here you can see quantity 1, then using the information, then select card info, and then buy compute minutes. I accept buy compute minutes, and this is how you can buy the additional compute minutes. So now, as we do have enough compute minutes, these instance runners are ready to perform the task assigned from our CI/CD configuration file. Here we can see gitlab-ci.yml file. This is our configuration file for CI/CD. Now, to add CI/CD environment variables, we'll go to project, and then from the project, settings, then CI/CD, and then from CI/CD go to variables, and here add the CI/CD environment variables like this, how we have set here. If I show, click on the edit icon, and then set the visibility to masked. This will hide the sensitive information to output during the CI pipeline run. So the variable will be protected, and this will be set by default, and then we'll have to provide the key and then the value. So these two, and we'll have to select the variable as must. Like this, how we'll have to set the CI/CD variables. Now, for collecting these two, the AWS access key ID and AWS secret access key, we'll have to generate an access key using the console of our IAM user account. So let's quickly see how we can generate one. Let's sign into our AWS IAM user account. AWS sign in to console. We'll sign in as an IAM user ID, password, ID, username, ID, password, and then let's sign in. We'll provide the MFA code from our authenticator app. Seven, 5, 7, 3, 3, 7. Sign in. And then we'll go to this account ID at the top right, and then go to the security credentials, and then scroll down a little bit, and then from here we will create a secret access key. We have created one. Let me show how we can create another, then others, then next, then provide a description. This is the access key. This is the access key. Let's provide any description of your choice according to your need, then create access key. So the access key has been created. Now we can download the .csv file, which will include the secret access key ID and the value. So let's download. Now we can see here the access key and secret access key ID and the secret access key. Now we can use these two in here as secret access key ID and the secret access key as our CI/CD environment variables in GitLab. And then for the Docker username here, it will be the Docker Hub username. If we go to the Hub Docker and sign in there, we have created an account here already. So we'll quickly sign in with Google. You can see this is our Docker Hub username, Docker username. So this will be the Docker username here. From here we can collect this one. And for the Docker access token, let's go to account settings, then click on personal access token, and here you can see we do have already a Docker access token created. Let's see how can we create another one. Generate new token, then provide the name. Let's set on 2, and then set it to expiration date none. This will be none, and then provide read, write and delete access to the token, and then generate, and then use this secret access key, copy this secret access key and use it to here as a value here, like this. How So once we set these variable values, this will be fetched dynamically during our CI/CD pipeline run. In here, if I show here, these are the variables which will be fetched from here during the CI/CD pipeline run while automating our deployment to deploy our application in the AWS cloud. You can see here this 4, with this 4 we have used $, which specified this as the environment variables. So let's move on. So far we have created necessary accounts in AWS, have configured GitLab and Docker to run our CI/CD pipeline to automate the deployment process. Now it's time to set up the environment in the AWS cloud so that we can deploy our microservice application there securely. And for that, we are going to create some networking related prerequisite resources. Before creating these resources, let's first understand how the environment will be formed with all the resources that we are going to create to run and function our application securely there in the AWS cloud. Let's open the architecture diagram for the AWS that we do have for our setup. We can find this one in GitLab also. It's attached there. Here we can see the architecture diagram for the resources of what we will have primarily on the AWS cloud. And we can see we do also have the request and the response flow from the outer world to the application resources. This is the VPC, the virtual private cloud, which creates a logically isolated network for all the resources within the cloud, ensuring secure and private networking. We can see all the requests and the responses from the outer world needed to go through this internet gateway within the VPC, which provides an upper layer of security. And within the VPC, we'll have subnets to segment the VPC, which will provide isolated private networking for each virtual machines we create to run our application. This segmentation enhances security, improves network performance, and allows better control over the traffic flow and resource allocation. And this internet gateway, we already know about this one. It is to enable subnets to communicate with the internet. For example, it allows incoming request from the browser to travel through the internet and reach the Kubernetes nodes running on the virtual machines within the subnet. And there's a route table which is connected with the subnets and the internet gateway. It defines the routing rules, means where to route the traffic between the subnets for the internal communication. One example for the internal communication is when subnets share resources with each other. Let's say this subnet needs to access the data of the MongoDB database of this subnet. And for this type of internal communication within the VPC between the subnets, the route table is used to route the traffic to the right destination. And the route table is also used for the outbound traffic from the subnets to the internet gateway. The outbound traffic from the subnets to the internet gateway to reach the internet for the external access. This can be for any necessary updates for the resources, pulling container images into the Kubernetes clusters, connecting to external services outside of the VPC, DynamoDB table, S3 bucket for external storage. And there will be virtual machines as per we configure the number and size. We have two, you can see. These virtual machines will have the EKS Kubernetes cluster installed and configured to run our application. These virtual machines can also be referred to as EC2 instances. Now let's talk about the Elastic Kubernetes Service EKS cluster. This cluster automates the management of all the resources of our application services, ensuring seamless scaling, deployment, operation, and execution of workloads while eliminating the need for manual intervention. And we can also see here the security groups. This will act as firewall rules which will define allowed traffic for each resource running on the virtual machines. And then there's network ACLs. These will also act as firewall rules, but at the subnet level, which will control, means allow or deny the inbound and the outbound traffic for the subnets. And there is DHCP option sets. DHCP stands for Dynamic Host Configuration Protocol. When an EC2 instance starts, means virtual machine starts, it automatically requests an IP address, DNS settings, and the other network configurations from AWS managed DHCP service, eliminating the need for manual setup and ensuring seamless communication within the VPC network. Now see, within the VPC, we have two subnets, and within each subnet, there will be one virtual machine, EC2 instance, acting as a server to host our application. Kubernetes will run on these virtual machines, managing the application resources and ensuring efficient deployment, scaling, and operation. Since these EC2 instances will be responsible for running the application workloads, they are referred to as worker nodes in the Kubernetes cluster. Additionally, a Kubernetes control plane or the Kubernetes public API server managed by the EKS will oversee these worker nodes by handling networking and resource management. And lastly, we do have two external services outside of this VPC, which are the DynamoDB table and S3 bucket. This DynamoDB table ensures safe concurrent access to the state files stored in the S3 bucket. The state files stored in S3 bucket track infrastructure changes, making it easier to manage updates. For example, if our application experiences increased traffic, we may need to upgrade the virtual machines type for more CPU and RAM, or scale up the number of virtual machines to handle the extra load. Let's say we need to increase 3 or 4, like this way. And then since the state files in the S3 bucket contain details of the previous infrastructure configuration, they provide a clear reference for analyzing the changes. This makes it easier to determine what needs to be updated and ensures a smooth and accurate infrastructure modification process. So these are the prerequisite networking resources from the AWS cloud, which are going to be needed before we deploy our application there on the cloud. Now that we have got all the resources introduced, which we will have in the AWS cloud to deploy our application, it's time to create the resources. First, we will create the prerequisite resources by running these Python scripts. Here we can see there are 3. Here these are the prerequisite resources: the VPC, and then the internet gateway, the route table, DHCP option sets, and AWS managed network load balancer. These come along with the VPC. And then the subnets. the network ACL comes along with the subnets, and then we will create this Kubernetes cluster and the S3 bucket during the automatic deployment of our microservice application by running the CI/CD pipeline, and the virtual machines or the EC2 instances are going to be launched automatically after creating the Kubernetes cluster. The necessary security groups will also be created automatically after creating the cluster and launching of the EC2 instances. Now, before running these Python scripts in the AWS managed integrated terminal, we'll have to authorize that also. It's called CloudShell. So let's go to the AWS Console, and then let's open the CloudShell into new tab. Now run AWS configure, hit enter. Now provide the infos accordingly. This is the AWS access key ID. We'll collect the access key ID and the secret access key from the .csv file, which we have downloaded after creating this IAM user account. I have done it before. Now don't want to expose the secret, so just paste the ID and secret key here, and then here also provide the default region, and then for the output format just hit enter. We don't need to provide anything for that. The output will be in JSON format by default. So as our CloudShell authorization is also done, we can run all the AWS CLI commands here. So now let's create the resources from the CloudShell using these Python scripts one by one. Let's start by running the first script to create VPC, subnet, and the internet gateway. By default, the route table, this route table, network ACL, security group, DHCP option sets will be automatically created along with this VPC. So after executing the first script, all these marked resources will set up and ready to use. Also the internet gateway. All these marked resources will be set up and ready to use. And we will verify the creation from the VPC dashboard. From the VPC dashboard here, where we will be able to see the created resources along with the numbers. So let's upload the first file and run according to this heading section into the CloudShell. Here, CloudShell. Let's upload from here, actions, then upload file, then our project is this one, and the Python files are here inside of this folder, task before after CI/CD, and this one the first script. Let's upload this one. File has been successfully uploaded. Let's check that. Yes, we can see the file here uploaded inside of the CloudShell. Now we can run it. to run that, we will run it according to the heading section here, Python 3, and then the file name. Let's hit enter. Nice, nice, this is nice. So the required desired resources have been created successfully. You can see with the VPC ID, the public subnet IDs, and it is also saying VPC public subnets setup complete. Let's first collect this VPC ID from here. And the public subnets IDs also, and place this into the right place to specify our VPC and subnet inside of the terraform.tf file into our project here inside of the config folder, then Terraform AWS EKS, then this one, the file. So Terraform is infrastructure as code, means we specify the cloud infrastructure or the resources as code, like here in the main.tf and here terraform.tf file. Here we can see all the resources are specified in an organized manner. We will talk about this more later before running the CI/CD pipeline. Now let's quickly place the VPC ID and subnet IDs into the right place inside of the terraform.tf file before we run our CI/CD pipeline and create the resources there in the cloud. So VPC ID, VPC C45, let's check that again, VPC C45, yeah, it is okay. Now subnet 0b, subnet, two subnets. So the first one is subnet 0b, subnet 0b, let's check that again, subnet 0b. Now the second one, subnet 5b, let's paste it on here for the second subnet, subnet 5b. Let's check that again, subnet 5b. So the VPC ID and the public subnets IDs are correctly placed here inside of this terraform.tf file. Now we can run our CI/CD pipeline, and before that let's quickly check what are the resources we have created from the console in here inside of the VPC dashboard. We'll have to refresh. Nice, we can see one VPC, two subnets, one route table, one internet gateway, then one DHCP option sets, then network ACLs, one network ACLs, one security groups. So we have the VPC, subnet, and other networking related resources, as we said earlier, using our this architecture diagram. Now let's upload the this second Python script to generate the EC2 SSH key pair. Let's upload this one and run according to the heading section inside of our CloudShell. Preparing the terminal. It is okay. Now let's upload the file. Second one. ls, yeah, the file is there. Now let's run. Copy this command, hit enter. So you can see key pair MERN micro app key pair created and saved to MERN micro app key pair.pem. Private key file permissions updated for MERN micro app key pair.pem. So the key pair has been created successfully. Let's go to the ECT dashboard and see. From here, EC2, dashboard, we can see the key pairs. Here's one key pair. The key pair, this SSH key pair consists of a public and private cryptographic key, enabling secure passwordless authentication for remote access to an EC2 instance. If I go to the AWS architecture diagram, for example, when the browser sends an HTTP request to the app URL, it reaches the EC2 instance here running the application. If remote management is needed, the SSH key pair public key on the EC2 instances and the private key with the user provides secure password-free access, allowing the user to connect to the instance via SSH. Currently, we don't have any EC2 instance. See from the VPC dashboard, refresh. We don't have any EC2 instance running, but we will be launching 2 during the deployment as per our pre-configured cloud infrastructure in Terraform. If we go to our code and Terraform and then terraform.tfvars file, you can see the initial node count is set to 2, which means there will be 2 EC2 instance or virtual machines will be launched after the deployment, and we specified also the machine type, which is m6i.large, available in the AWS cloud. Now that we have created the SSH key pair successfully for the EC2 instances by running the second script, it's time to run the last one, this third one, to create the DynamoDB table for safely concurrent access to the state files about which we have discussed before. Let's upload the file, this third one, and create the DynamoDB table. CloudShell. Let's clear the terminal and let's upload third one. Upload it successfully. ls, the file is there. Now let's run. So we can see table Terraform state log created successfully. These are the information about the table. So the DynamoDB table has been created successfully. Let's go to the console and see. Console, DynamoDB. Then we'll go to tables. See, here's the table which we have created. Terraform state log. The table is active right now. So let's move on. Now that we have set up all of these necessary networking resources into the cloud, it's time to move on to the CI/CD pipeline process to deploy our application to the cloud, utilizing these networking infrastructure resources which we have created. And for that, let's go inside of the .gitlab-ci.yml file, and here, which holds the configuration of our CI/CD pipeline. We can see here we do have two stages, build stage and the deploy stage. The build stage here will build the microservices as Docker images, in other words, the advanced build version. And after finishing the build, it will push these Docker images to the Docker hub. Like here, we do have the repositories, image repositories, and the images inside of the repositories, so that later we can pull those images of this kind to run in the cloud as Docker containers after configuring with the Kubernetes for the deployment and for the scalability with the resources which we want. And here we can see the deploy stage, where we will be deploying our built Docker images. Here we'll be installing the necessary packages, and then we'll be authenticating to the AWS cloud, and then we'll be creating the remaining infrastructure using the Terraform, like the Kubernetes cluster and the storage bucket. As we can see here, we do have the configuration for Terraform initialization and for applying the Terraform code to create the infrastructure resources inside of the AWS cloud. So let's see what we do have inside of our Terraform code. So for that, config folder Terraform AWS EKS, then here we can see here with this code we are configuring the bucket to store the state files. The state files will store info of the Terraform state, means the resource create information for each Terraform apply will store that in the state files. And then we are configuring the Kubernetes cluster, which creates public cluster with managed node groups, enabling public endpoint access, and then auto scaling and necessary IAM roles. And then with the variables.tf file, we are defining variables with the necessary information, and with the terraform.tf file, we are defining the variable values. So this was the short description for the Terraform code. And finally, we are deploying our build microservices or images which are configured with the Kubernetes manifest files. You can see here under of config folder, then KTS. You can see from here. These manifest files are for configuring the deployment resources, such as setting up number of replicas, CPU memory, request limits, and then configuring the replicas to expose as a network service to enable the communication with other replicas for the external access. This was for the comment microservice container, and the others are also configured almost like the same way. You can see here these are also configured like the same way. So let's back to the CI pipeline here. So after this stage, we'll have our microservices running as containers, means as the Docker containers. And the Docker containers include build applications and its packages, and they operate on the host machines OS and kernel for the file management and network handling, which makes the containers lightweight, efficient, and platform independent and also portable. Now, here in this Kubernetes architecture diagram, we can see that the services exposed as TCP, which we saw before, which enables two-way communication for all the microservices to receive requests and respond to the outside world, including the browsers, and also for communicating between the microservices with each other. We can see they are communicating with each other. These services will create pod with one replica, as we saw before. So the pod count will be 1 for each one. Here we can see for all the services there's one pod associated, and which will hold the relevant service resources or the build packages and will act as deployed containers, which we were talking about inside of our CI pipeline. So Kubernetes will manage these resources, this pod, ensuring they run smoothly, scale when needed, and update automatically. The pods serve as the deployment unit, ensuring the services are highly available and scalable within the Kubernetes cluster. We'll talk more about this Kubernetes architecture diagram later. So this was all about the automated CI pipeline, and then the infrastructure as code Terraform, and then the Kubernetes deployment configuration for our application, and about the deployed containers, which we already have talked about. Now, to push the code in GitLab, we do need to add an access token here in GitLab, and then need to set the origin of our Git remote using that access token from our local machine, which will give us the permission to push our local code to the remote project here in GitLab. So let's quickly create an access token from here in GitLab. To do so, we'll go to settings, then access token, and then add new token. Provide a proper name. We'll pick this one, and then provide proper description. We are not going to provide any right now. And then we can see the expiration date is set to 1 month from today, and then provide the developer role, and then we'll select all the scopes for the developer role. And then create project access token. So I have successfully created our token. We need to store this token securely. Now we will set the origin to connect our local with this remote project in GitLab. To do so, come back here in VS Code, then instead of the integrated terminal, we'll type git remote set URL origin, then we'll collect the HTTPS URL from here, then paste it on here. Then we will use our access token in here inside of this URL. After https:// then / then before of gitlab.com, paste it on here. Then we will provide @ before of gitlab.com. Now the origin can be set. Now hit enter. So we have successfully set our remote origin. Now we can push the code there in GitLab from here our local PC. Now let's quickly push the code and trigger the CI pipeline in GitLab. To do so, we'll git add all, hit enter, and then git commit m let's commit as updated VPC and submit IDs in Terraform.tf verse for AWS app deployment. Let's commit and then git push. GitLab will ask for the authentication. Sign in with browser. Let's authorize git credential manager. Now the pipeline should trigger. Yeah, it's triggered. Let's monitor it. Build jobs are started. We can see the build job has started running with 4 different segments. Let's wait for successful builds. Let's monitor inside of here. Let's wait until it finishes. So 3 jobs are done successfully, build jobs for comment service, post service, and the query service. Now it's time for the front end. Let's refresh the page. Let's see. Let's wait. So the front end build is also done. We can see job succeeded. All the jobs are done, and meanwhile the deploy job has started, we can see. So let's monitor it and wait until it finishes all the tasks assigned. Installations are done. Authentication to AWS is also done. The bucket has been created. Terraform initialization has done. Terraform plan is done. Now creating the remaining infrastructure. This is the plan, Terraform plan. It is done, yeah. Now creating the remaining infrastructure on AWS by the Terraform apply. Let's wait until it finish. It is started creating the EKS cluster, Kubernetes cluster. It will take up to 5 to 7 minutes. So let's wait until it finishes. So finally the EKS cluster has been created. You can see it took almost 11 minutes. Okay. Now it started creating the node grooves. Let's see how much time it takes. So node grooves are also created, and finally deploying our containers, cleaned up unnecessary files, and done the deploy job. Job succeeded. So the full CI/CD pipeline has been successful. We can check the output logs of the CI pipeline by taking proper time later. So the deployed job is done, and we have created all the required resources and successfully deployed our application on the AWS cloud. Now it's time to validate the resources which have been created after our CI/CD pipeline run. Now, before validating the resources created during the automated deployment of our application in the AWS cloud, we need to set up the eksctl and configure it to connect and manage the EKS cluster by the eksctl commands from AWS CloudShell. So from here, the CloudShell, let's first set up the eksctl, and to do so, we'll use this command to download the eksctl first. It's downloaded, and then we'll use this command to extract it. It's extracted, and then let's verify the installation first. eksctl version. It's showing the version, so eksctl has been installed successfully. Now let's update the kubeconfig to access the EKS cluster by eksctl commands from here. Use this command. This is the cluster name we can see here, and this is the region which we have set before. So let's hit enter. So the kubeconfig has been updated successfully. Now we can run eksctl commands in here from the CloudShell to manage our EKS Kubernetes cluster. Now let's validate the resources which we have created by the CI/CD from here in this CloudShell first. The primary application resources are pods and services. Let's check the pods first. kubectl get pods. This has listed all the pods that we have, we can see, showing their readiness, status, and restarts, which helps us to verify if they are running properly or not. We can see all the statuses are showing running, which means all the pods are running successfully without any issue. Let's see the diagram. If I show from here in this architecture diagram, these are the pods we can see here. These are the pods that we have listed in the CloudShell here: post service, comment service, query service, and the front-end service, pods for the application microservices, and then the post Mongo, comment Mongo, query Mongo for relevant database pods, and then there's one RabbitMQ pods there we can see. These pods are the smallest unit in Kubernetes, representing a running instance of a microservice, or we can say the small deployed version of a microservice. Here each pod contains one or more containers we can see with the necessary application code and dependencies. In our case, one container per pod, as we have configured in our Kubernetes manifest files, which we have shown before. Now let's check the services. kubectl get svc services, and this has listed all the services that we have, showing their types, assigned IPs, and then external access points, which ensures that our deployed microservices are accessible. Now if I show from here in this architecture diagram, these are the services we can see. Services. So these are the services. Post service we can see here, comment service, query service, then front-end service, then the database services, post Mongo, comment Mongo, query Mongo, and also there the RabbitMQ service we can see. So these services are a way to expose pods. We can see it's exposing the pods. So these services are way to expose pods, ensuring stable networking. They provide a fixed access point. Here we can see the access point. We tried to demonstrate the access point like this way. They provide a fixed access point to allow communication within the cluster or with the external world. Here all of these application and database services are exposed as cluster IP. We can see we have application microservices are cluster IP. We can see here the type is assigned as cluster IP, and aside of it, each cluster IP service has assigned IPs. This represent that these services can only communicate and share data with other services which are inside of this Kubernetes cluster. For example, the post service here, the post service can share data and communicate with the comment service, the query service, and also the RabbitMQ service, and also the 3 database services, as all of them are defined as cluster IP here we can see within the cluster. However, it cannot communicate with the external services outside of this cluster here. Outside of this cluster, it cannot communicate with the external services. For example, if I show the AWS architecture diagram here, Here we can see the post service from here, it cannot communicate, which is a cluster IP, cannot communicate with the DynamoDB table. The post service resides in here. It cannot communicate with the DynamoDB table or the S3 bucket, as these are the external services outside of this Kubernetes cluster. And then there's, we can see one RabbitMQ service, which is defined as load balancer, we can see. Now this can share data and communicate with all of these cluster IP services inside of this Kubernetes cluster, and can communicate with the external services, such as from here, if I show, with this DynamoDB table and S3 bucket outside of this Kubernetes cluster, the RabbitMQ service also can communicate, as the RabbitMQ service is defined as load balancer. So now with this RabbitMQ service, we don't need to communicate with the external services like DynamoDB table or S3 bucket, but we need to access that in our browser here outside of this Kubernetes cluster. We need to access that so that we can show the RabbitMQ management UI, see the connection queues and also the others associated with it. And that's why we exposed the RabbitMQ service as load balancer, not cluster IP, just to show the RabbitMQ management UI. So these were our main resources which were introduced using this CloudShell, and also the architecture diagrams. Now we are going to see and validate the infrastructure related resources from the AWS Management Console, which have been created after the CI/CD. For that, let's go to the VPC dashboard from the console, VPC, and here VPC dashboard. From here, the running instances are 2. We can see we do have 2 EC2 instances launched inside of the VPC network. So from here, if I show from the AWS architecture diagram, here we can see we do have 2 EC2 instances. So 2 EC2 instances have been launched. As we have said before, that these 2 EC2 instances will have the EKS cluster, Kubernetes cluster installed and configured to run containerized workloads. As a result, these standalone virtual machines or EC2 instances will function as worker nodes responsible for running and managing containerized workloads, executing Kubernetes pods, handling application deployments. And then from here, we can see in security groups, 4 more new security groups has been created. This will be managed automatically by the AWS. Now let's go to EC2 dashboard. Here you can see instances. The instances numbers are 2 here. This represents the total number of instances launched, which is 2, and instances running. This represents currently 2 instances are running, about which we have already said. And then auto scaling groups, here we can see this auto scaling groups in AWS automatically adjust the number of EC2 instances, these EC2 instances, based on the demand, ensuring that our application has the right amount of compute resources, and thus it will help us to optimize the cost by managing the resources automatically based on the demand. Now load balancers. After launching the EC2 instances, these EC2 instances as worker nodes, an AWS managed network load balancer, this one here we can see from this diagram, is created evenly distribute incoming traffic across these instances. which ensures high availability and optimal performance. Now let's see what is inside of this load balancer. You can see with its internet facing scheme, the load balancer routes external traffic to the two EC2 instances running in different availability zones. So the zones are US East 1A, we can see, then US 1B, then US East 1A. So these two zones which we do have. The VPC and the hosted zones identifiers here define the network setup, ensuring the traffic management and seamless routing across the cloud infrastructure. Here we can see the load balancer we have been discussing, also referred to as AWS Managed Network Load Balancer. It routes both inbound and the outbound traffic, efficiently. Inbound traffic includes requests and responses from the kubectl for managing the cluster. And the outbound traffic includes fetching necessary resources updates, pulling containers, images, and connecting to external services through the internet from the Kubernetes cluster via the AWS Network Managed Load Balancer. So this routes the outbound traffic from the Kubernetes cluster to the EC2 instances and then all the way to the internet to pull images or to connect to the external services. This ensures smooth traffic flow and seamless communication between the Kubernetes cluster and external resources. Now, this was the load balancer. Now we can see here we do have volumes. Volumes in AWS refers to block storage that provides persistent storage for EC2 instances, which allows data to persist even after instance termination. And then under instances we do have launch templates here. The launch templates in AWS are pre-configured templates that define the EC2 instance settings such as AMI, instance type, key pair, security groups, etc., making it easier to launch and scale the instances consistently. Then we'll see Amazon S3, then general purpose buckets. So here we can see the required bucket created, which will store the Terraform state files about which we have said before. If I show the created state files from here into the bucket and then into the Terraform state and then version, we can see here we will have all the different versions of the state files here. Now if I go to the IAM and then IAM dashboard, from this dashboard we can see for the users we do have one IAM user previously created and then roles and policies. We initially had two roles that are just auto created in the root account for the AWS support, and those are AWS service role support and AWS service role for trusted advisor. See here the AWS service role support we can see, and then AWS service role for trusted advisor. So now 6 roles, except these two, 6 more roles here. So 6 new more roles have been created to support the newly provisioned resources, along with one new policy here we can see, along with one new policy which has been created. Here we can see. So this roles and policies work together to define permissions and access controls for the IAM user, which we created before this IAM user, which ensures secure and efficient resource management within the AWS. And then there's one identity provider. So after deploying the Kubernetes cluster, an identity provider was automatically created because EKS uses OpenID Connect OIDC for authentication, and OIDC is a protocol that enables secure token-based authentication without relying on long-term IAM credentials. This identity provider allows EKS to securely connect external services outside of the VPC. Such as DynamoDB table or S3 bucket. So using this identity provider, the Kubernetes cluster will be able to access the external services, DynamoDB table or S3 bucket. And then let's go for the Kubernetes cluster, Elastic Kubernetes service. From here, under of clusters, we can see we do have one cluster which will control, manage, operate, and run our containerized microservices to automate and scale, and thus it will ensure the high availability and efficient resource management. If I show from here, we can see the public EKS cluster here. This one is created. Now let's check what are the resources that we do have here. Under the resources here, we can see all the resources are listed by their types. If I expand the workloads here, we'll be able to see all the created application workloads here. Right now, as this application is simple with the workloads, we will be more interested about the pods. We can see pods which are responsible for running and functioning the application, and there all the other resources also been created here: cluster, service and networking, then storage for authentication, service accounts, and then policy. So we can check also these by taking enough time. So these are all the resources which have been created after the deployment of our application on the AWS cloud by the CI/CD. Now, as the deployment is done, it's time to expose the application to the internet and test that on the browser. And for that, first we'll have to get or register a domain from any of the domain providers out there. It can be from domains.squarespace.com or hostinger.com, namecheap.com. If we register from Squarespace for 1 year from here, domains.squarespace.com, it can cost around 12 to 15 USD per year. We have a registration on the domains.squarespace.com named as microsvc.net. You can see for 1 year, with which we are going to work further. See, this is our domain from Squarespace showing the status active. You can see. So we will have to register a domain of our choice, and after registering a domain, we'll have to wait for a few minutes to up to 24 to 48 hours for the domain to become globally available. Domain providers will notify us about it through email. As we have our domain and it's currently active, so it's globally available and we can work further with it. Now, as we have our domain, we'll now apply for an SSL certificate from the AWS Certificate Manager. So let's go to the console home, and then from here, Certificate Manager. Then from here, click on request, then request a public certificate. The next, then for fully qualified domain name, we'll put svc.net. So we'll add another domain to this certificate, which is *micro-svc.net, micro-svc.net, *micro-svc.net. So it's correct. Now this asterisk sign, you can see here, this asterisk sign will allow to support all the subdomains under of the domain micro-svc.net. So now let's go to validation method. Here DNS validation recommended, keep it as it is. Then key algorithm RSA 2048, keep it as it is. Now lastly, request from the bottom right. So we have created our certificate. We can see the status of the certificate is pending for validation. It is because we haven't linked this certificate with our main domain yet. So after we link this certificate with our main domain, we'll get our certificate status issued from the pending. So let's quickly add a DNS record there and then talk about after that, because otherwise the AWS will take too much time for provisioning this certificate. So let's quickly add the DNS record first and then talk. We'll use this prefix and then DNS record, add DNS record, then cname custom 300, then alias data, so a custom record was saved. So we have added a custom DNS record here using the cname for our main domain provided by this certificate. Here you can see this cname was for our main domain. So we have used the cname for our main domain. This prefix we have used as a host. Here we can see this prefix before of .microsvc.net, and then we have used the type here, type cname from here, and then we have used full cname value without the last dot or full stop. So we have used that in here as a value or data value. So now this should link our main domain with the certificate, and it can take up to 30 minutes to couple of hours to get provisioning to be active, or even less. For example, can take a couple of minutes to active or issued the certificate. So once we have the certificate status issued here, and each domain status gets success, will ensure that the certificate is issued by the AWS and successfully linked with our main domain. So these are in pending state right now. Let's refresh the page. So nice, we have successfully issued our certificate, and the status for the domains are also gets success. So you have successfully obtained an SSL certificate for getting secure HTTPS connection with a registered domain. And one thing forgot to say here about the TTL. We have used TTL 300 seconds, means 5 minutes, because for faster DNS updates during testing we use a lower TTL. Like here we have used example for 5 minutes, to quickly reflect the changes, because we need that, because we are testing. It is not for production. For better performance, we set a higher TTL, for example 4 hours, which is suggested by the Squarespace, to reduce DNS lookups and server load. So this was the TTL, and we have successfully obtained an SSL certificate for getting secure HTTPS connection with our registered domain. Now that our SSL certificate is successfully linked with our main domain, it's time to get the main domain up and running by deploying our application on it. To achieve this, we first need to enable external access and configure HTTPS routing. For this, we will be deploying a Kubernetes manifest file called app Ingress YAML, which will handle the Ingress routing for us. Now, if I deploy this file, the Ingress managed network load balancer will be automatically created. We can see from here, from this architecture diagram, it will be automatically created because of these following configurations here, where the Ingress class name here, this Ingress class name specifies that the AWS application load balancer should be used, and these annotations here, these annotations define how the AWS ALB should be configured, such as ALB Ingress Kubernetes IO scheme here, internet facing, makes the ALB publicly accessible. Then with this one, Kubernetes IO certificate ARN enables SSL TLS certificate for HTTPS connection. Then license port, with this one, Kubernetes IO license port, this configures port 80 for HTTP and 443 for HTTPS for the load balancer. And then these defined rules here, we can see these defined rules. So these defined rules and backend services, these are the backend services used. We have used our backend services: post service, comment service, query service. So these rules and backend services specifies which service the load balancer should route to. Here we can see the path we have used. Here we can see the ALB will route traffic to the post service, comment service, query service, and the front-end service. Based on the URL paths, API post, API/comments, API/query, and the route path for the front-end service. And it also handles a redirect rule for www.microsvc.net, sending traffic to the route path here, which is this microsvc.net. For the route path will serve the front end. So for the route path, using 301 redirects, using this rule. After this redirect rule, let me show you. Let's say we do have www.microsvc.net. Now if we hit enter on this, if we hit enter, it will redirect to https microsvc.net. So if we enter the URL www.microsvc.net, it will redirect to the microsvc.net route path and with secure connection with the prefix of HTTPS. And this redirection was needed because some businesses are still using www for branding, consistency, or for technical reasons, which leads the users to often start their branding searches with the www prefix. So to maintain a modern, standardized experience, this redirection removes the outdated www and enforces a secure HTTPS connection by having the prefix of HTTPS in the replacement of www. So this was about the redirection from www to the HTTPS secure connection. And from here, to function these Ingress resources and configurations specified in this Ingress file, the Kubernetes will need to have an application load balancer controller along with the application load balancer. If we see from this architecture diagram here, we can see load balancer and this is the controller. So we will have this Ingress load balancer once we deploy this Ingress file, but this Ingress controller needs to be installed and configured additionally. We will talk about how this Ingress load balancer and controller both work together to route traffic to the application services and then to the pods from the browser to the pods, services and then to the pods. Let's talk about this later after we successfully set up the Ingress and access our app on the browser. Now to set up the Ingress, we need to deploy it first, and before deploying the Ingress file, we need a little bit of modification, which is we need to replace this ARN with the correct one from our issued SSL certificate from here. So we will copy the correct URN for our SSL certificate and then we will paste it on here. Delete this one for our certificate. So now let's first deploy this Ingress file, and to deploy, let's upload this one inside of the CloudShell. Here is our CloudShell. Let's wait to connect. Now let's deploy the file. Upload file, config, app ingress, open. Successfully uploaded. Let's check that. App ingress YAML is here. Now let's deploy that by kubectl apply f-f then app ingress.yml. Hit enter. This is configured. We can see Ingress networking, app ingress created. So we have deployed all the specified Ingress configuration along with the application load balancer ELB. Now let's check the status by kubectl get ing. We can see the status is, we can see we don't have any address yet, external address yet. It is obvious because we need an Ingress controller, means ALB controller, to get out of this empty address place, and we will have inside of this place the assigned address for this Ingress. So once we have that address, we'll be able to access our application successfully. So for that, we need the Ingress controller. To install the Ingress controller, we'll be following these installation instructions for the Ingress controller under point 5. So under point 5 we'll be following these installation instructions for the Ingress controller. And these instructions can be found from this text file called manual one-time task after cicd.txt, which is stored inside of the root directory of our project. Now let's quickly follow it and install the Ingress controller. So first install Helm. Let's install the Helm. The Helm installation is done. Now let's check the version. So yeah, version 3.17.2, so it's okay. Now let's install the Ingress controller using the Helm repo add EKS. EKS already exists with the same configuration, skipping. Looks like this was already there because earlier when I tested things, so this was there already. So let's move forward with the next task, which is Helm repo add update. It's updated successfully. Now let's install the Ingress controller. ALB Ingress controller installed successfully. Nice. Now eksctl get pods and queue system. Let's check the status of the pods. All the pods are running 0 by 1. Let's check again. Yeah, now it's okay. So all the pods are running and ready. We can see here. Now it's time to create controller IAM policy. IAM create policy file load balancer. So we'll be needing this file. So it will need to this file upload. The file load balancer controller JSON can be found inside of the folder here. This one. So this file holds the policies which are needed to the Ingress controller. So let's create the controller IAM policy using this JSON file. So first we'll upload this file into the CloudShell. Let's upload that one. Upload file inside of the root directory, then task before after cicd, then this. The file has been uploaded successfully. Let's check. JSON file. Yeah, this one is the JSON file. Let's clear the terminal. Now let's copy this command and create the controller IAM policy. The policy has been created. You can see the policy name, policy ID, MERN. Now list the node groups. This is the node groups ID, we can see. Now find node group role. Cluster name, node group name. Okay, we'll have to paste this one. Sorry, this was the node group's name, not ID. So we'll have to put this name at there. Let's modify that. Copy this one to find the node groups role, and then we'll paste this node group name there in place of here. Now we'll copy the command and paste it on here in the Cloud Shell, then hit enter. We can see this one is the node group role. Let's copy it and paste it on here for further use if we need. Then this will return something like this. Okay, the role has been stored as we will like. Okay, so we have collected the role and stored it in here in the notepad. Now attach the policy to the IAM role. You'll have to attach the policy. For that, your node group role, we have collected this one and then AWS account ID. Okay, now let's copy this one to attach the IAM policy, and let's modify that command in here for your node group role. This is our node group role. Let's copy this one and paste it on here, and we do also need the account ID. Let's copy our account ID from here. You can see this is our account ID for our IAM user. Let's copy the account ID and let's paste it on here. So the command has been modified. Now let's run it on here. The validation error when calling the attach role policy operation, the specified value for role name is invalid. Okay, the role name is invalid. Why? Let's see what has been done wrong. ARN. Copy your node group role. Oh, we have copied the full ARN, not our node group role. Node group role will be role slash, after slash we will have the node group role. So let's check that here. So this one will be our node group role. We have copied the full ARN. So let's modify this one. This one is right now is correct. Now let's copy it and paste it on here. Node group name. Now let's copy that. Role name. Yeah, this is correct. Now let's paste again in here. So right now it is okay. So we have successfully attached the policy to the IAM role. Now to verify the policy attachment, we'll copy this command. Do we need any modification? Yes. AWS account ID. Let's copy this one and modify it on here in our notepad. We do have our account ID copied before. Let's copy it and paste it on here. Now we'll run this command inside of our Cloud Shell. Let's copy that and let's paste it on here. So this was for verifying the policy attachment. So we can see the policy has been attached to the role name, this role, and this is the role ID. Now find your subnets. Do we need any modification? No. Let's find our subnets. We do have already the correct cluster name there. Let's find our subnets. This is our subnets. We could collect that from our Terraform also. Tag the subnets. Subnet ID. So let's copy this command to tag the subnets, and let's modify the command in here. We'll copy the first subnet ID and paste it on here, subnet 0a. Let's subnet 0a. Yeah, it is correct. Now for the second one, subnet bc. Subnet bc. So yeah, it is also correct. Now we can run this command. Let's run this command. So this was for tagging the subnet. So the tagging of subnets is also done. Now let's verify the tagging. Value subnet id. We again need to modify these two commands. For the subnet id, this one will paste it on here for the first subnet, and then for the second one we'll copy and paste that on here. Now we'll run this command, these two commands, to check the tagging. Yeah, we can see the tags. So the subnet tagging is okay for the first subnet, and for the second subnet, yeah, for the second subnet it is also okay. Now attach EC2 full access permission to the IAM role. To attach the EC2 full access permission to the IAM role, we will copy this command. We need to modify this one. Let's paste that on here. Now your node group role, our node group role is this one. So let's copy that and paste that on here. And now let's copy this command and paste that on here. Now let's hit enter. It is done. So the attachment of EC2 full access to the IAM role, to this IAM role, is also done. Now the next we have to do is we'll have to restart the ALB controller to apply the changes we have made above to the configuration. Okay, before doing that, let's check again the kubectl get ing. So the Ingress controller is not reflected yet on the Ingress. So let's restart it. kubectl rollout restart deployment AWS load balancer controller. After restarting, we should have our Ingress controller running. So after restarting the Ingress controller, we took a little break, less than a minute, and checked again the Ingress status and saw we got our Ingress ALB address. You can see here. So we can see here the ALB address has been assigned to our app Ingress. Now we can move forward to set up the DNS record for our app domains, main domain and the subdomain for www. And for that we'll be using this ALB address there in the Squarespace. So let's go to the Squarespace DNS settings. For adding the custom records, we'll add record, then instead of this host place we will add @ and then type will be alias, and then TTL will be 300 seconds, and then the data will be the ALB address from the Ingress. let's copy this and paste this one in here. Now let's save. So the record has been added successfully. Now let's add another one to get the www subdomain. And for that, let's keep host as www, and then type will be cname, and then say 5 minutes per the, okay, 300 seconds will be for 5 minutes. Then alias data should be this ALB address. Now let's save. Here we can see these below two records are added for the main domain and the subdomain. This @ here, this @ will result to our main domain, which is microsvc.net, and this www will result to our subdomain, which is for www.microsvc.net. And the type alias here, the type alias is for the main domain, and the type cname is for the subdomain, and the TTL has been set to 5 minutes for the both. And lastly, the data value is set to the ALB address obtained from the Ingress previously from here. Now, as the DNS records are correctly set up, now let's open git bash to check and validate the DNS records. Git bash. Now we'll check our main domain. To do that, ns look up microsvc.net. Now let's hit enter. Nice, it's getting the IP, which means the domain has been recognized and now it's globally available. Now let's check for the subdomain, which is for www.microsvc.net, ns www. then microsvc.net. Let's hit enter. It's also getting the IP, we can see it's also getting the IP, which means the subdomain has also been recognized and now it's globally available. Now we can also validate the propagation of the DNS records from if we go to the URL, let's copy the URL from here. If we go this URL, and then if we type our domains here, microsvc.net, then look up DNS, so we can see the microsvc.net is correctly propagated and it's globally available. So let's test the subdomain also, then look up DNS. It is the subdomain is also now propagated and it's globally available, which is validated by the DNS lookup online software. You can see the CNAME and the types. So our domain, main domain and subdomain is correctly propagated. Now it's time to test our application on the browser. Let's go for that. Now to test our application, let's check our main domain, which is app domain. In the browser URL, we'll type microsvc.net and we'll hit enter. We have misspelled the micro is VC. Now it's correct. Let's hit enter. Nice. The app domain has redirected to secure connection with HTTPS. See, the URL is now consist of HTTPS. Here the browser is also saying the connection is secure, you can see. Now let's check our subdomain with another tab. We'll type www.microsvc.net. Now we'll hit enter. See, subdomain is also working with the prefix www. And see, the subdomain with www. Prefix is resolving our main domain, which is microsvc.net, and also getting redirected to the secure connection with HTTPS. We can see the connection is secure. So both of the URL are working for our main domain and also the subdomain for www. Now it's time to test our application and its functionalities. This application simulates a simple social media style interaction where users can create messages referred to as posts. Let's create a post. You can see this is referred as post, and add messages under them. So we can add messages under the post which can be referred as comment. We can see this is post and this is comment, and this is just a simulation of a social media style interaction. So each post here, each post and comment represent a piece of data that must be stored in a database and retrieved for display. Let's refresh. We can see the data, post data and comment data, these are coming from the MongoDB database. So that is why if we refresh our page, the data are not getting lost. So we are retrieving the data from the MongoDB database. So the goal is to illustrate how the microservices communicate by efficiently handling creation, storage and retrieval of this data, which we refer to as post and comment. We can create more. We can create more post, second post, and we can also add comments under that. We can see the data are coming from the database. So once a post or comment is created, it is stored in a database and later fetched to be displayed on the front end like this. How? So to efficiently manage these functionalities, the application follows a microservice architecture like this. How? Inside of the Kubernetes cluster, consisting of the following services: post service, comment service, query service, front end service, where the post service manages post data creation, comment service manages comment data creation under post, then query service acts as a message broker, temporarily storing and managing communication between services from the post and comment service to the query service to ensure seamless data flow. We do have the microservices such as post service, comment service, query service, and the front-end service, where the post service manages post data creation, comment service manages comment data creation under the posts, query service retrieves and stores both post and comments data, and then the RabbitMQ service acts as a message broker, temporarily storing and managing communicating between services from the post and then comment service to the query service, which ensures seamless data flow. Then front-end service fetches data from the query service and displays it. Now, to gain a clear understanding of how these microservices interact and function, we will complete this following task here. First one is reviewing the project structure and code, and then the second one is demonstrating the code and app workflow through practical scenarios, and the third one is demonstrating the app workflow through the live logging. So let's go for that. Let's go for the first one to review the project structure and code. Here's the project structure we can see, and the microservices, front-end service, post service, comment service, query service, and there is one config folder we can see, inside of which we do have the configurations related to the Kubernetes for the app workloads, and then there is Terraform configurations for defining infrastructure. We have talked about all of these configurations before, so now we just want to focus on the application codes related to the microservices only. Let's start with the backend services first. Here the post service, comment service, and the query service, these three services are the backends for this application, a microservice application. For the post service, the index.ts file inside of the source folder will be executed first. Then it will first search for the router module. We can see router from the Express.js framework. So it will first search for the router module, then it will find the module in here inside of the routes.ts. Inside of the routes.ts it will find the router module. Then here this router.post method is not going to perform any task initially, because it will only execute when there will be any post request made with the endpoint /API/post. Means this method will execute when we will create any post from the front end. So initially this router module is not going to do anything. Then let's go back to the index.ts file. Then after this startup method will be called. After that it will try to connect to the MongoDB database service to the default port. We can see 27017 for the database named post. Once it's processed, then lastly this will start the API server. We can see app.listen. This will start the API server on port 5000 for the post service. We can see here, and then it will log this message to the backend. This was for the post service. Now for the comment service, the index.ts file will be executed first, as the post service. Then it will first search for the router module. Then it will find the router module in here inside of the routes.ts. It will find the router module. Then here the router.post method, this router.post method is not going to perform any task initially, because it will only execute when there will be any post request made with this endpoint /API/comments/ the generated post ID, randomly generated post ID. Means this method will execute when we will create any comment to any specific post from the front end. So initially this router module is not going to do anything. Then let's go back to the index.ts file. Then startup, it is called in here. Then this startup method will be called, and after that it will try to connect to the MongoDB database here to the default port 27017 for the database named comment. You can see once it's processed, then it will try to connect to the message broker service RabbitMQ to the default port 5672 as the MongoDB service. So this piece of code here, this piece of code for the RabbitMQ related to RabbitMQ is not going to perform any task, as initially there won't be any message published from the post service to the RabbitMQ, and then it will log, lastly it will log the message to the backend after starting the server to the port 5100. This is for the server for the comment service. And then for the query service, The index.ts file will be executed first as like the post service and the comment service, and then it will first search for the router module. It will find the router module in here inside of the routes.ts file. Then here this router.get method is not going to perform any task initially, because it will only execute when there will be any get request made with this endpoint /API/query. Means this method will execute when we will fetch all the database records through the backend of the query service by accessing the root path from the frontend by the browser. And this is how it is designed. So initially this router module is not going to do anything. Then here, let's go back to the index.ts file. Here the startup method will be called. Then inside of the startup method, it will try to connect to the MongoDB database first, to the default port for the database query. Then once it is processed, then it will try to connect to the message broker RabbitMQ to the default port as like the MongoDB service. This piece of code, query comment queue, query comment queue, query post queue, this piece of code related to RabbitMQ is not going to perform any task, as initially there won't be any message published from the post service as well as the comment service to the RabbitMQ, this RabbitMQ. So lastly, this will start the API server on the port 5200 for the query service. We can see here for the query service, and then it will log the message, this message, to the backend. So this was all the backend services: post service, comment service, query service. These three were the backend services. Then their front end also, we will talk about it to our next point when we will be demonstrating the code and app workflow through practical scenarios. Then we will talk about the front end more. And we have already talked about the configurations. So this is our whole project structure. Now let's go for the second task. So the second one is demonstrating the code and app workflow through practical scenarios. So to better understand the internal and external communication and the data flow within the application through practical scenarios, let's break it down into three key scenarios: accessing the application, creating a post from the front end, adding a comment to the post from the front end. So let's go for the first one. When accessing the application, what happens when we access the application? When we access the application in our browser with the app URL, browser sends a GET request to the Ingress, our app Ingress. Then from our app Ingress, the Ingress managed load balancer, here ALB, which is used here, receives the request and forwards it to the Ingress controller, which then routes the request to the front end service here for the root path, because we have used the root path with our domain here. See, redirected to the main domain. For the root path, it redirected to the main domain, our host. So the front end service receives the request. Then to respond, the front end service then under pages index.js, the front end service then starts its execution from index.js under of the pages folder. Then the first get server side function runs first, attempting to fetch data from the query service. We can see. So the flow here will be like, request flow will be like, the browser's JavaScript runtime environment leverages the built-in fetch API. This is the fetch API to initiate a default GET request from the front-end service, from this front-end service to the query service. because we are making GET request to the query service. Query service we have defined here instead of the fetch URL. So this is possible because the front end and query service are within the same Kubernetes cluster, which we also saw before. With this architecture diagram, if we see the front end service and the query service both resides inside of the same Kubernetes cluster, and because of that it is possible to use internal name like the query service and port to directly reach the query service from the front end service, bypassing Ingress since the request stays within the cluster. So inside of the query service, routers.ts, the router.get method for the /API/query endpoint we can see. So the router.get method processes the request, receives from the front end service, retrieving all the records from the query model collection within the query database we can see. The MongoDB schema here, MongoDB schema for this collection is defined within the service to ensure structured data storage. Let's say for post service, comment service, so this will be stored in a structured way. So for fetching the data, the query service will respond 200 OK status, returning all the retrieved records to the front-end service. The front-end service processes the response and returns a fully rendered HTML page with the paged data embedded as props. Here we can see it will return embedded props data, and it is returning a fully rendered HTML, and this is possible because of server-side rendering SSR, which improves initial load times by reducing the need for additional client-side rendering. So this get server-side props function is returning from the front-end service a fully rendered HTML page received from the server. Then the browser receives a fully rendered HTML page. The browser receives a fully rendered HTML page with the preloaded data and displays it, because browser has made the GET request by accessing the application. So it lastly then receives the request from the front-end service. So now given that the query database is initially empty, because we can see here we just received this portion, we just received this cut, and under of this post and comments we have created later. So initially we will receive this cut. So as we receive an empty array, we will not have any post and comments, we'll just have this cut. So let's explore how the front end handles this scenario, which is query database is initially empty when we access the application. So how the front end service handles that scenario after receiving an empty array. Let's explore that from the code. Since the query service is initially empty, the query service responds with an empty array. Then this empty array is then passed to the home component. From here to here, this home component. So it is passed inside of the home component, where it is stored inside of the state for further processing. The create post here inside of the return statement, the create post component renders an HTML page here, renders an HTML page displaying a create post heading, then an input field with a placeholder text saying post, then a create post button underneath of it. Then go back to the index file, then the list post component then renders a small HTML template displaying text no post available, since the data length is 0, because when accessing the application we receive an empty array from the query service. So then we will have the data length as 0. and that's why this block of code will not execute. This will execute, and which will say no post available. And after that, after applying some CSS styles, from here we can see global CSS, home module CSS. After applying some necessary styles from here, for this cut, the front end completes its processing, and then it returns a response which is received then by the browser, because we made the GET request from the browser. So this is how the front end service initially communicates with the backend and responds to the browser here when accessing the application. Now let's look at what happens when we create a post from the front end. When we access the application from the browser here, the front end is downloaded and cached inside of the browser. Now when we create a post by clicking the create post button here, you can see. So when we create a post by clicking the create post button from the front end in the browser, here instead of the code, so by clicking the create post button, we create a post. When you do that, the onSubmit function triggers, then onSubmit function triggers a post request to the /API/endpoint, sending the post data through the Ingress as we discussed earlier, like this. How if we go to the Ingress here, instead of the app.ingress, we can see the /API/post. So the request will be routed to the Ingress, and then the Ingress will receive this request and it will route this request to the post service, to the /API/endpoint by the load balancer controller. So the request will be routed to the post service, then the post service will receive this request from the Ingress. Let's see where this /API, yeah, we can see this endpoint is here instead of the routes.ts file. So the post service will receive this request and processes the post data by generating a unique random ID, and then saves the post inside of the MongoDB database, post database. And after saving it, it connects to the RabbitMQ, a message broker, and creates a temporary storage called post exchange. Here we can see the post exchange using the channel assert exchange. The processed post data is then published to the temporary storage or the post exchange, which makes it available for the other services to consume. For example, here if the comment service and query service also subscribes to the RabbitMQ, then they will also can consume this message which is published to the post exchange. So before moving on to how the response is returned to the front end, let's look at what happens inside of the RabbitMQ. So as the query service here is also connected to the RabbitMQ and listens for new messages, we can see it is connected to the RabbitMQ, listens for new messages. As the post exchange currently holds only post data, RabbitMQ creates a bind queue called query post queue. Here we can see query post queue. So this queue is binded especially for storing post related data. The query service processes this post message, adds an empty comments array. This processes this post message and adds an empty comments array and saves the processed post message inside of the MongoDB database. Here from here, empty comments array, it adds an empty comments array to the post, and then it saves the post inside of the MongoDB database. As a result, the query database now contains the same post data as the post database of the post service, ensuring all inputted data from the front end is properly stored. Now let's go back to the post service to return the response back to the front end. Is this the post? So the RabbitMQ processing is done. Query service received the data from the RabbitMQ and it stored the data, the post data. Now after that, the post service finally responds to the front end in the browser through the Ingress. So the response will be sent to the front end again back via the Ingress. Let's see, go back to the front end again. Yeah, now the response is sent to the front end, and then the response res.data here is modified by adding an empty comments array. Here we can see, then the new data is created by appending this new post to the existing list here. Then the refresh data updates the my data state in the index.js here instead of the index.js. So then the new post dynamically appears in the list as the state updates. This triggers a UI re-render updating the DOM in the memory or RAM. Now let's talk about how the data persists here. Since the DOM exists only in memory, once the page is reloaded or closed, the DOM is recreated. The frontend is re-downloaded upon accessing the application again, and the post data is fetched from the query database through the query service, ensuring persistence. In fact, not just this post data, we are visualizing all posts in the front-end service sourced from the query database via the query service. So this completes the entire flow of creating a post, processing it in the backend, storing it, and dynamically updating the front end from here. Now let's explore the process of adding a comment to a post from the front end. Let's create a comment. This is second comment. So like this way. So when we access the application from the browser, the front end is downloaded and cached, as we know. Now when we create a comment by clicking the create comment button like this way on a post, let's see what happens inside of the code. Go to the front end first. In here, create comment.js. So when we create a comment by clicking the create comment button, this onSubmit function triggers, and then it makes a post request to the /API/comments, and then the post ID. This post ID will be dynamically replaced with the post ID to which we are creating the comment. So to this endpoint, this onSubmit function is making a post request to the comment service. The comment data is sent through the Ingress as we discussed earlier. The comment service receives the request and processes the comments data. Then so the comment service will receives that request, post request, and then it will process the comment data by generating an unique comment ID. It then saves comments data inside of the post message object in the database. Here we can see this is the post message object. So the comment is stored inside of the post message object. So the comment is saved inside of the post message object in the database, linking it to the correct post ID. After saving, the comment service connects to the RabbitMQ, the message broker. Then it creates a temporary storage called post exchange, and then the processed comment data is then published to the post exchange, making it available to the other services. Here the query service will listen to this post as it is connected to this exchange. Now before we discuss how the response is returned to the front-end service, let's look at what happens inside the RabbitMQ. The query service is also connected to the RabbitMQ and listens for the new messages. So let's see inside of the query service. So the query service is also connected. Here we can see connected to the RabbitMQ and listens for new messages. Since the post exchange currently holds only comment data, RabbitMQ creates and binds a queue called query comment queue to store comment related data. The query service processes the comment data from here. The query service processes the comment data, adds it to the correct post here, adds it to the correct post, and saves the updated post inside of the MongoDB database. Here the query database. Now the query database contains the same comment data, ensuring consistency across the system. Now let's go back to the post service to return the response back to the front-end service. So here inside of the comment service, the comment service finally responds with the process comments data including unique comment ID. Then the response travel back to the front end in the browser through the Ingress, where the response, let's say here inside of the front end service, the response have reached here. This is the response. Then the response res.data in here is modified by publishing a new comment into the comments array of the specified post. The updated post structure will look something like this. Here we can see the post data will have an array for the post. Inside of that array we'll have the post object. Then inside of the post, along with the post ID, we'll have the comments array. Inside of the comments array we'll have the comment here along with the comment ID, randomly generated comment ID. So the structure, updated post structure will look like this. Then new data is created and appended to new comment to the existing post list, and then refresh data here, refresh the new data, refresh data will update the my data state in the index.js here. The new comment will dynamically appears here in the list as the state updates by this refresh data function. This triggers a UI render updating the DOM in memory or RAM. Now let's talk about how the data persists here. Since the DOM exists only in memory, it resets when the page is reloaded or closed. When the user accesses the application again, the frontend is re-downloaded. The comment data is fetched from the query database along with the post ID belongs to through the query service, ensuring persistence. In fact, not just this comment data, we are visualizing all posts and comments in the frontend service from the query database via the query service. So this completes the entire flow of creating a comment, processing it in the backend, storing it, and dynamically updating the frontend. Like it is dynamically updating the frontend. Let's add a third comment. So like this, how it is dynamically updating the frontend. Now we are going to talk about the third one, which is for demonstrating the app workflow through live logging. Before we do that, let's first access the user interfaces for the MongoDB database and the RabbitMQ message broker to visualize the data from the MongoDB and the RabbitMQ servers. So to access these two management UI services, we do have the necessary setup here. For the RabbitMQ configuration file, we have defined the service as public facing load balancer, then have exposed it via necessary port, and the same also for the Mongo Express. Here we can same also for the Mongo Express configuration file for accessing the user interfaces via load balancer IP and their ports. Now once we deploy these two configuration files, the relevant user interfaces will be exposed to the outer world and we'll be able to access those with their assigned external IPs. If I go to the CloudShell, let's get it connected. Now let's run kubectl get parts, and then services SVC. We can see here we already have deployed these services. Here, if I show from here, this one is for the Mongo Express deployment, and this is for the RabbitMQ deployment, and this is for the RabbitMQ service, and we are having the external IP, and this is for the Mongo Express service. We are having the external IP for both. Now let's try to access the UIs using these assigned external IPs and also with ports. Now let's try to access the MongoDB UI first from the browser. Let's copy the external IP and let's paste it on here, then colon. Then let's see for the Mongo Express what we have used as port 8081. Then have provided the colon, then let's paste the port there. Now let's hit enter. Nice. So now we can access the UI with the local port 8081. We can see here, we can see the query database, which is our app's central database, and here we are not going to access the post and query database just to make it short. Here we can see the query database. Let's view it, and then we can see the queries collection. This is the query database. This is the query collection. Let's view it. Now under of the query database, we can see here under of the query database we do have the collection queries, and under of it we will have our required data, means all the posts and comments we can see here. And it's our app central database. We can see here post, and then under of it we do have the comments here and here. If we expand it, we can see. So under of post we do have comments, and there's also the post ID. We can see all the posts, and there's 2 posts back. There's 3 posts we can see, and then the relevant comments for that post. Here 2, here 1, here 3. So we can see here the post, and then under of the post all the comments which are created earlier. So this looks nice. We'll use it later in time of demonstrating our application through the live logging. Now let's move on to access the RabbitMQ management UI. We'll go to the console again. Now for the RabbitMQ, we will copy the external IP, then we will paste it instead of the browser's URL bar, then we'll put a colon, and then we'll collect the port for it, which is 15672 for the HTTP port. We are accessing this under of HTTP, so let's put that port and hit enter. Nice. So now we can also access the RabbitMQ management UI. Here we can see under the exchanges a post exchange. Here a post exchange is created, about which we talked earlier. This post exchange functions as a database similar to what we observe in the MongoDB UI, and the queues from queues and streams. The queues in this context act as collections about which we also have talked earlier. The queues, here we can see query comment queue, query post queue. So the queues temporarily store the published data to the RabbitMQ exchange, to this exchange, enabling specific services to communicate and share information. So this was about the MongoDB and the RabbitMQ UI to illustrate the underlying mechanisms showing how data is managed within the system before we go for the live testing for our app through the live logging. Now let's first check all the pods logs one by one to see if they are operating successfully or if there's any issue before going for the live logging. Let's modify these commands, and for that let's collect the actual pod names which are there, kubectl get pods. Now let's copy this actual pod names from here and paste it on here. Now let's modify these commands with the actual pod names. For the first one, post depl, let's collect the pod name for the post depl. This one is the post depl. Now let's replace that. Now for the second one, comment depl, let's collect the comment depl. The first one is comment depl. Let's copy this one and paste it on here, replace that. And then the third one is query depl. Where is query depl? This one, the last third one, query depl. Then the query depl is replaced. Then after the query depl, for the post mongo depl, this one is the post mongo depl. Now let's replace that also. Then for post mongo depl, after post mongo depl, for the comment mongo depl, let's replace the comment mongo depl. Now for the query mongo depl, let's collect the pod name query mongo depl. This one is the query mongo depl. Let's replace that also. Now RabbitMQ stateful set, this will be as the same as it is. Now for the front end depl, we'll collect this pod name and paste it on here. So we have formed all the commands to see the pod logs. Now let's check the logs from the backend services first one by one, and for that let's separate the backend services. Post depl, comment depl, query depl, these are the backend services. Then post mongo depl, comment mongo depl, query mongo depl, these are for the MongoDB services, for the relevant backend services. Then RabbitMQ, then front end. So we have separated the backend services. Now let's run post depl. Now let's see the log for the post service. Let's paste it on the CloudShell. Now let's check. So post service listening on port 5000. So the backend server has been started successfully, we can see, and we can see all the other logs. It's connected to RabbitMQ, then the post saved post to DB, so it's running successfully without any issue. Now let's check the logs for the comment service, second command. Now let's paste it on CloudShell. So the comment service is listening on port 5100. So the backend server for the comment service has been started successfully without any issue. We can see the other ports while we posted comment, say comment API connected to RabbitMQ, then saved post. So this comment service is also running successfully without any issue. Now let's check the pod for the query service. We can see query service is listening to port 5200, and the other logs also successful logs. Comment message acknowledged, successfully saved comment to DB, post ID, processing comment message. So all the other logs are also there. So this query service is also running successfully without any issue. So all the backend services has been running and functioning successfully for our microservices without any issue. Now let's see the logs for the MongoDB services for each backend services quickly. Let's see those quickly, if there's any issue or not, or they are running successfully. So we can see no issue with the MongoDB database for the post service, so it is okay. Now comment Mongo. So no issue with the MongoDB database for the comment service, we can see. Then the query service, query Mongo, No issue with the query Mongo service also. Now let's check the RabbitMQ. So no issue with the RabbitMQ service also. We can see here authenticated, granted access to vhost. So no issue with the RabbitMQ also. And then let's see the front end. Actually, we don't need to see it. We can check it from here. The front end is working. So this is actually for logs. We can see all the comments and posts are showing on here instead of the logs. So it is also running successfully without any issue. We can see the IDs, comment IDs, post IDs, all the comment IDs and post IDs. So let's see from here what else remaining. Maybe post express DEPL, it is missing in here. Let's check the logs for it also. Now let's run it in here. Let's clear the CloudShell. Now let's check the logs for the Mongo Express. So it is also running without any issue, we can see here. So all the individual pod logs we have checked and every pods are running successfully without any issue. The statuses are also okay, running and ready one by one, one by one, one by one. So everything is okay here. Now we can move forward. So now let's see some real-time logs generated by the application workloads to illustrate the app workflow. And before we do that, let me show you one thing. I have deleted all the pods here, kubectl delete pods all. Have deleted all the pods to reinitialize everything so that every logs can be generated initially, and the data which are inside of the databases for post Mongo, comment Mongo, and the query Mongo central database, all the database will be initialized from the beginning. So there will be no data because we have so far inputted quite a little bit, quite much data from here. So the front end was messy before, now it is clear. And also from the MongoDB UI, we can see there's no query database right now. So once we input any data from the front end, the query database, the database will be connected to the query service, and also the query database will be created, and that we'll be able to see the data in here inside of the MongoDB UI. So everything is initialized from the beginning. There's no data. Now we'll be able to illustrate things easily through the live logging. So now kubectl get pods. Let's restart the query DEPL again, otherwise it will create problem. kubectl, if we restart it again, it will perfectly connect to the RabbitMQ service. kubectl delete pod cl, kubectl get pods. Now everything should be perfectly fine and our app should be working correctly. Now let's update these commands here for the backend services. We'll ignore these logs for the post Mongo DEPL, comment Mongo DEPL, for the MongoDB database logs and RabbitMQ logs. We are going to ignore these logs because these are not needed and necessary for us. These won't show anything. So the backend services, post, comment, query, and the front end, these pod logs are necessary for us to see and visualize the data flow inside of the application. So we'll see the live logs for these pods only for the backend services and front end. Now let's copy this and paste it in here in replacement of this. Now let's update the pods for the backend services. Post DEPL updated, then comment DEPL, then query DEPL, then the front end. So These commands are now okay to run in CloudShell. To see the live logs, let's paste the commands in here and see our live logs. So we can see it's generating all the individual service logs that we have seen earlier here, and showing the front end is currently empty with the response text. We can see this is the empty array which we have got from the query Mongo database, from the query service about which we have talked earlier. So now let's create a post from the front end. We will keep these two windows side by side to visualize things easily. Now let's create a post for real-time logging, post for real-time logging 1. Let's create this post and see what happens in the real-time log. Create post. Yeah, nice. We can see for the post service and the query service, we can see the live logs. So the post has been saved to the DB post Mongo database, then the post service connected to RabbitMQ, then it's created RabbitMQ channel, then it's asserted the message, and then it's published the message to the RabbitMQ. The post service published the message to the RabbitMQ to route to the comment service and also to the query service. We can see the message routed to the query service, post message, processing post message from RabbitMQ. After publishing the message, query service is listening to the message and then processing the message from the RabbitMQ. After processing, it logged the message ID, we can see. Then it is showing successfully saved post event to DB. Then it saved the post message to its DB. Then it's saying the message post message acknowledged. Okay, nice. Now let's come in here in the front end. Finally, in the front end, we can see the first one. We can see the ID and then the post and our message real-time logging 1. And along with that, we can see there's a comment with an empty array. So there's no comments, just a post, which is post for real-time logging 1. Post for real-time logging 1 with no comments, which is comments with an empty array. So everything is working as expected. We can see here in the live logging. Now let's see the MongoDB UI which stored our post message in here. Keep real-time logging in here. Let's refresh the page. We can see the query database created. Let's view it. Collections, let's maximize this one. Collections, view. We can see our post data here. Post for real-time logging 1 and post ID, and there's no comment we can see. So there's just post. So this was for the post. Let's create another post and see what happens. Yes, let's create another one. This is for post 2. The second post created. Let's see what happens in the live logs. Yeah, message saved to TV, then connected to RabbitMQ like before. Created channel, asserted RabbitMQ exchange, published to RabbitMQ to route the message to the query service, then query service processing the message from RabbitMQ, then received post message and it's generated an unique ID, then successfully saved post event to DB for post ID, then it's saying post message is acknowledged because it saved the post message to its central database, to the application central database. Now let's see in the front end. The front end should retrieve the data from the query database. Let's see fast log here. Along with post real-time logging 1, there should be another one, post real-time logging 2. We can see here post real-time logging 2 with an empty comments array. So there's no comments, and that's why empty comments array. So here also everything is working as expected. Let's see the MongoDB UI, refresh the page. Now we'll be able to see our second post also with empty comments. Now let's create a comment inside of our first post and see what happens. Create comment. This is first comment. Let's create the comment. Create comment. Nice. It is generating the live logging. From the comment service we can see comment ID saved to the post which we have created before for the post real-time logging 1, the first post. To the first post we can see the ID. Let's check the ID in here. This should be in here. The post real-time logging 1, this is the ID 982E1D2. So we can see this one 982E1D2. So this is the post ID. To that post ID the comment is created. It is saying comment, and this is the comment ID generated. Comment saved to the post to which it is created, and then it is saying comments API connected to RabbitMQ, then exchange created, then comment published to the RabbitMQ, so that the query service can also listen to the comment message. So the comment is routed to the query service, then query service received the message, and then it is saying processing comment message from the RabbitMQ, and then received comment message with the ID and post ID. So the comment is received in query service, then query service successfully saved comment to the DB for post ID. So the query service saved the comment to that post to which it is created, then query service saying comment message acknowledged, like the post. So this is nice. And then front-end, the front-end service response text up to here. Now we should see the comments array here. The comments array which was empty before, it should be updated with the comment which is created here. Now let's see for the first one. Let's see the first post real-time logging 1. This is the comment, this is the comment, and the comments array updated which was empty before. This is first comment. We can see, so this is nice. And for the second post we can see the comments array is still empty. Now let's create another comment in the first post. We will see the second comment also in here. So it's generating the logs like before. Let's see the comments array. The first log for the first post real-time logging 1. Now this is first comment. Oh, the both comment is named as like same. This is first comment, this is first comment. Okay, no problem. We will be able to see two comments there. Yeah, here we can see this is the first comment, and also this is the first comment. So there's two comment inside of the comments array right now. We can see for the first post. From here first comment, then the second comment here named as the same like the first comment. And for the second post here we can see for the second post for real-time logging 2, the comments array is still empty. Let's input a comment and see. This is first comment for the second post. Let's create that. The comment is created. Let's see the live logging. The logs are generating like as before. Now let's see what it shows. This is first post, and then this is the second post real-time logging 2. Now we can see the comments array has been updated for the second post, for this second post. So everything is working here as expected. And oh, let's see the MongoDB UI. There's no comments array here still. We'll be able to see 2 comments for the first post and 1 comment for the second post. Let's refresh the page. See, there's 2 comments for the first post and 1 comment for the second post. Let's expand it. We can see this is first comment, and the second comment also named as the same like the first comment. So there's 2 comment. Now let's see the second post. We can see this is first comment for the second post. So everything is working here as expected. So this is the data flow. Where we illustrated how the application interacts with the backend microservices to process and visualize data on the front end in real time through the live logging. Now, to connect everything for the application with all the resources together, we will now try to have a look at the architecture diagrams that we do have for the traffic handling between the infrastructure resources, for the data flow while accessing the application, for the data flow while creating a post, and for the data flow while creating a comment. Let's start from the beginning. With the infrastructure related resources. Here, let's see what happens when there's an inbound traffic to our web app services running inside of the Kubernetes cluster. For example, when we are accessing the application, for this we can see the red lines here. We try to represent the data flow when we are accessing the application with the red lines, we can see. So when we enter the app domain in the browser first checks its local DNS cache to see if the domain's IP already is resolved or not. Since this is our first access attempt, it won't be found. Next, the OS checks its system-wide cache and host files for manual mappings. As none exist, it proceeds to the next step. Then the OS sends a DNS query to its configured DNS resolver, typically provided by the ISP, means the Internet Service Provider. On my PC, I checked the settings here and found that my default IPv4 DNS server is 192.168.0.1, which refers to my router. And checking further, I found the DNS servers 8.8.8, which refers to the public DNS service from Google, and 1.1.1. This refers to the public DNS service from Cloudflare. Our ISP uses these DNS servers to resolve domain names. So then, one of the ISP provided DNS resolvers, which is the fastest and most responsive from these two, Google and Cloudflare, for our case will query the authoritative DNS servers or the name servers where our domain is stored along with its IP, which we are searching for. In our case, if we go to our domain provider here, domain name servers, we can see nscloud.googledomains.com. So our domain provider is using the name servers from Google. So in our case, these name servers will store our domain globally along with its IP. So from here, the fastest and most responsive name servers from our case will return the resolved IP address to the DNS resolver here. And then from these two, one of the DNS resolver, it can be Google's public DNS resolver or Cloudflare's public DNS resolver. So from these two, one of the DNS resolver then sends it back to the browser here. Then after the resolved IP is returned to the browser by a DNS resolver, it processes with that IP further to establish a connection with the web server that resides in the Kubernetes cluster. And to send and receive responses to resolve these DNS to IP, the browser uses the TCP IP stack to establish connection, where TCP breaks our data into small packets and IP assigns addresses so that they can travel independently. At the destination, TCP reassembles the packets, which ensures reliable data delivery and transmission. Since our request is over HTTPS, a TLS handshake is also performed to establish a secure communication channel. So after receiving the public IP, which is exposed externally to access internal resources managed by the Kubernetes cluster, so after getting the IP, the browser sends an HTTPS request to the public IP on port 443. As this IP is hosted and exposed by the Ingress in the AWS cloud, the request gets permission to enter into the AWS global infrastructure. AWS identifies the VPC to which the IP belongs to. The internet gateway then allows the traffic to the route table as the destination IP is valid and routable within the VPC. And then the route table routes the traffic to the correct subnet where the destination IP resides after getting permitted by the network ACLs. Next, the request is received by the VM, virtual machine, within the subnet after being allowed by the security groups, either here or here, where the VM is already configured via DHCP, an AWS managed service which ensures seamless communication without manual setup. So after receiving the request, the VM forwards it to the Kubernetes cluster hosted on the VM itself. To route traffic to a web service inside the Kubernetes cluster, the VM uses AWS managed network load balancer to route traffic to the Ingress here, matching the destination IP with the exposed IP. The Ingress then routes the traffic to the responsible service inside of the Kubernetes cluster, typically the front-end app. The requested resources is then returned as a response following the same backward path back to the browser. The response flow will be like from Kubernetes cluster to the security groups, and then VM or worker nodes network interface, then network ACLs, then subnet, then route table, then internet gateway, then the browser through the internet. And here we have drawn the lines for the response flow, like as the request flow. To avoid redundancy with the diagram, we can see here the response flow should be here from the AWS network load balancer to the security group. After being permitted by the security group, it should be inside of the VM, then VM to the network ACLs. After being permitted by the network ACLs, it should be inside of the subnet. Then from the subnet, it should go to the route table. Then from the route table, it should go to the internet gateway. So here we have kept like this from AWS network load balancer to the VM before of security group, where the traffic should go to the security group and then VM. So we have kept like this to avoid redundancy. Otherwise, we'll have to draw like this from AWS network load balancer to the security group, then this. So for the request and response flow, there would be too much lines and it would be hard to understand the request and response flows with this diagram, and that's why we kept like this way the responses as like the request flows. So here this was the flow when accessing the application in the browser, and for inputting any data from the browser, for example when we create post or comments, the request and response flow will be the same as when we access the application, but there's no need to resolve the DNS again, as it will be already resolved when we first access the application. And here for the reliable data transmission, the TCP IP stack is used here or utilized. Additionally, since the request is over HTTPS, a TLS handshake is performed to establish a secure communication channel. So this was the flow for the inbound traffic when we access our application from the browser, and also when we input any data from the front end in browser. For example, it can be creating post or for creating comment. Now let's go for the second inbound traffic, which is for kubectl request and response to manage the resources of the Kubernetes cluster. Here we have represented this traffic flow using the green line we can see here for the kubectl request and response. So when we update our kubeconfig file, let's say we are using CloudShell instead of a browser. So when we update the kubeconfig file using the AWS CLI command, the command will look like this. This command retrieves the Kubernetes API servers, the Kubernetes API servers, external IP or DNS endpoint for accessing the cluster, and then it updates the kubeconfig file with that information. Once the kubeconfig update is successful, we have the IP address of this API server. We have the IP address or DNS endpoint of the Kubernetes control plane stored here. Now we run a kubectl command from our terminal or from the AWS CloudShell in the browser. The flow will be like the kubectl command sends an HTTP request to the Kubernetes API server's external IP because it is stored here, which was configured in the kubeconfig file. And then to reach this destination here inside of the Kubernetes cluster API server, the request from here, the request enters into the AWS Global's infrastructure and first hits the internet gateway of the VPC. And then the internet gateway forwards this traffic to the route table here. Green line we can see, the green line. So internet gateway forwards this traffic to the route table. Then the route table routes the request to the appropriate subnet where the Kubernetes public API server is accessible after being allowed by the network ACL. Next, the request is then evaluated by the security groups associated with the Kubernetes API server to ensure the request is allowed. The request is then forwarded to the Kubernetes public API server by the VM in which it is hosted. The server then processes the kubectl request, for example, request for retrieving application resources or request for applying configurations, etc. And then the server sends back the appropriate response, for example, the response status or the response for the requested resources. And then finally, the response goes back to the terminal or the CloudShell by the following reverse path from here to here to here, internet gateway, then the browser from where we are running the command inside of the CloudShell through the internet. So the reverse path will be like from Kubernetes API servers, security groups, VM or worker nodes network interface, then network ACL, then subnet, then route table, then the internet gateway, lastly the kubectl client here inside of terminal or CloudShell through the internet. So we have drawn the lines for the responses flow same as like the request flow we can see here to avoid the redundancy with the diagram about which we have talked earlier before for the fast inbound traffic. So this was the data flow for the second inbound traffic, which is for requesting the app resources while managing through kubectl. Now let's consider the outbound traffic generating by the Kubernetes cluster itself. We have represented this traffic using the blue line here we can see. So for the outbound traffic, when a service or pod inside of the Kubernetes cluster needs to access the public internet, for example, to pull container images during deployment, update resources, can be infrastructure or application related, or connecting with the external services outside of this VPC for data exchange, the request then follows this path. First, a pod inside the Kubernetes cluster generates an outbound request. The request is then forwarded to the worker node's network interface after being allowed by the security groups. Then the worker node forwards the request to the network ACL associated with the subnet. The network ACL evaluates and will allow this request, then it will reach the subnet where the worker nodes resides. After that, the route table associated with the subnet checks its rules and directs the traffic to the internet gateway. Then the internet gateway forwards the request to the internet. And then lastly, the request reaches its intended external destination through the internet. For example, Docker Hub to pull container images, external database servers to collect stored data, or third-party services like DynamoDB table, S3 bucket, or others out there to collect necessary information. So after processing the request, the external services then send back the response through the internet. So the response flow, the reverse path, like from the external services to the internet, and then the internet gateway, then route table, and route table to the network ACLs, then subnet, then from the subnet to the security groups, then from the security groups to the worker node, and lastly to the pod inside of the Kubernetes cluster which made the request. So as said before, like here we have drawn the lines for the request flow as same like the response flow to avoid redundancy with the diagram. So this was the flow for the outbound traffic. For this outbound traffic, so this was the flow for the outbound traffic when the pod inside of the Kubernetes cluster makes request for the resources from the outside world, from the internet. And another thing to mention is for the reliable data transmission here, for all the traffics, for the reliable data transmission, the TCP IP stack is utilized here for this traffic, for the outbound traffic, and also for all the types of traffic we have discussed, which include the inbound traffic, one routing request to a web app service within the Kubernetes cluster, then inbound traffic to requesting application resources via kubectl, then this outbound traffic handling updates, pulling container images, and connecting to external services. So for all this type of inbound and outbound traffics here, the TCP IP stack is utilized, where the TCP breaks our data into small packets and IP assigns addresses so they can travel independently. At the destination, TCP resembles the packets, which ensures reliable data delivery and transmission. And since these all requests are made over HTTPS, a TLS handshake is also performed here to establish a secure communication channel. So when we access the application in the browser, the request first undergoes DNS resolution. Once resolved, the request reaches the Kubernetes cluster, where it is initially handled by the Ingress managed load balancer. The load balancer then routes the request to the Ingress controller, which processes it based on the configured path rules. Since this request is for accessing the application, it matches the route path and is subsequently directed to the corresponding front-end service. We can see the red line is representing the traffic when we access the application. To the corresponding front-end service, we can see the type is cluster IP. So the front-end service then makes a default GET request to the query service to fetch data. The query service processes this request by retrieving data from the query database, which serves as the application's central data store. On the first access, the query database is empty, so the query service returns an empty array as the response. This response is then sent back to the front-end service, which processes and renders the data on the server side. Once ready, the response follows the same path back to the browser. So from the front-end service to the Ingress controller, and then to the Ingress managed load balancer, and then finally to the browser. So from this point onward, until the browser is refreshed, the DOM is maintained in the browser cache, allowing for efficient interaction. When users create posts or comments, subsequent HTTPS requests are made directly without requiring a full page reload. And here for the reliable data transmission, you can see we have mentioned here. For the reliable data transmission, the TCP/IP stack is used or utilized here. Additionally, since the request is over HTTPS, a TLS handshake is performed to establish a secure communication channel. So this was the flow inside of the Kubernetes cluster when we access our application from the browser. Now, for creating a post, we will already have the front end downloaded in our browser after accessing the application, and also the DNS will be resolved and the IP will be stored in our browser cache. So there's no need to resolve the DNS again until we delete our browser cache. Now we can create a post easily. So when we create a post from the front end, the browser directly makes an HTTPS request or the post request to the Kubernetes cluster, where it is initially handled by the Ingress managed load balancer. The load balancer then routes the request to the Ingress controller, which processes it based on the configured path rules. Since this request is for creating a post, it matches the /API/post path. The request is then forwarded to the corresponding post service, which is of type cluster IP. We can see this purple line, which is representing the traffic when we are creating post. So then the post service processes the incoming data and stores it in the post database for persistence. And simultaneously, it interacts with the message broker RabbitMQ, passing the post data so that the connected query service with the RabbitMQ can receive and process it. So after receiving by the RabbitMQ, the query service processes it, and then the query service stores this data inside of the query database, which serves as the central database of this application. This ensures that the newly created post can be retrieved along with the other stored data whenever the application is accessed. So returning to the post service, after successfully storing the post data in the post database, it returns the processed data as a response to the browser. The browser then updates the DOM in its cache, enabling real-time front-end updates without requiring a page reload. And then finally we can see our created post data in real time. So here, for the reliable data transmission, the TCP/IP stack is used. For the reliable data transmission, the TCP/IP stack is used or utilized. Additionally, since the request is over HTTPS, a TLS handshake is also performed here to establish a secure communication channel. So this is the flow inside of the Kubernetes cluster when we create a post from the front end in the browser. Now for creating a comment, as like before, we will already have the front end downloaded in our browser after accessing the application, and also the DNS will be resolved and the IP will be stored in our browser cache. So there's no need to resolve the DNS until we delete our browser cache. Now we can create a comment easily under of the post that we have created before. So when we create a comment from the front end, the browser directly makes an HTTPS request or post request to the Kubernetes cluster, where it is initially handled by the Ingress managed load balancer. The load balancer then routes the request to the Ingress controller, which processes it based on the configured path rules. Since this request is for creating a comment, it matches the /API/comment path. Here, this one, the golden one. The request is then forwarded to the corresponding comment service here, which is of type cluster IP. So this golden path, we can see this golden line which is representing the traffic for creating comment. So then the comment service processes this incoming data, and stores it in the comment database under the post that we have created before for the data persistence. So it stores the data for the data persistence inside of the comment database. And then simultaneously, it interacts also with the message broker RabbitMQ, passing the comment data so that the connected query service can receives and process it. So after processing, the query service then stores this data inside of the query database, which serves as the central database of the application. This ensures that the newly created comment can be retrieved along with the other stored data whenever the application is accessed. So returning back to the comment service, after successfully storing the comment data in the comment database, it returns the processed data as a response to the browser to render under the post created before. The browser then updates the DOM in its cache, enabling real-time front-end updates without requiring a page reload. And then finally, we see our created comment under the post created before in real time. And here, for the reliable data transmission, the TCP IP stack is used or utilized. Additionally, since the request is over HTTPS, a TLS handshake is performed to establish a secure communication channel. So this was the data flow inside of the Kubernetes cluster when we create a comment from the front end in browser. Now let's talk about data persistence. Earlier we stored posts and comments inside of the post database and the comment database while creating posts and comments. Even though all the data is ultimately fetched from the central query database, but why maintain separate databases here, like the post database or comment database? The answer lies in data persistence. If data is ever lost from the query database, the post database acts as a backup, storing all post and their associated comments, while the comment database retains only the comment related data. And this redundancy ensures that no critical information is lost. To restore the lost data in the query database, we can follow a structured recovery process called manual data syncing. This involves running a batch job or a recovery script that scans the post database for missing records and inserts them back into the query database, ensuring data consistency and integrity. Let's see here, instead of the config folder, then others, then this script, example db recovery script.py. Here's how a batch job or recovery script will look like for manual data syncing. We can see first it connects both the MongoDB database, PostDB and QueryDB, finds unsync records, then copies missing data, then marks records as sync here, then closes database connections. So this script ensures that if RabbitMQ fails, missing posts are retrieved from the post database and synced with the query database, from post database to the query database if the RabbitMQ fails or somehow we lost the data from the query database. So this was the approach to data persistence within the application, where we stored data in both individual connected services for posts and comments as well as in the central database. And this redundancy ensures that if data is lost from the central database, it can be retrieved from the individual connected databases, maintaining data persistence. And additionally, we demonstrated how this persistence can be effectively achieved using batch job or recovery script. This is how the script will look like, an example script it is. So we have covered describing the infrastructure, application and data flow along with the necessary diagrams. This is for creating comments, creating post, accessing the application, and then the infrastructure related resources where there was for inbound traffic while routing traffic to a web service running in Kubernetes cluster, e.g. accessing app, creating post, comments, and then for the inbound traffic to requesting app resource while maintaining through kubectl, then for outbound traffic, e.g. for updates, pulling containers, images, connecting to external services, the request is made by the Kubernetes cluster itself. So this was all the traffics which are related to the resources, infrastructure resources and the application inside of the Kubernetes cluster. So we have covered describing the infrastructure, application, the data flows, along with the necessary diagrams, explaining all components together to ensure a well-connected understanding. I hope this provides a clear and comprehensive overview of how all resources integrate and function within the application. Now, why do we need the microservice application and deploy it to the Kubernetes cluster in the cloud? Because the microservice applications are reliable after we deploy it to the Kubernetes cluster on the cloud. Let's see how it's reliable. Let's take an example to validate the reliability of the microservice application. When there's too much traffic coming to the application needs to scale to distribute the loads so that it can perform reliability without any issue. Let's get the pods first. Eksctl get pods. Here we can see all the pods which are representing the application are running. We can see all the pods are running. So the application is running fine without any issue. Now let's assume this post service, post depl, which is this post service is not working properly. The pod status is showing error. The pod status for the post service here showing error. Let's assume it. Or it can restart frequently. After analyzing the logs, let's assume after analyzing the logs and monitoring dashboards, we determined that there's too much traffic coming to the backend service, which is the reason for the pod restarts and the error. Now to resolve this, we need to increase the pod's resource limits so that it can have more CPU and memory to operate, and also along with that we can increase the pod's replica count, which will also be helpful to handle and distribute the extra load on the post service. So let's do this with the post service pod here. This is the post service pod. Now let's here increase the memory to 100 MI, 100. From 64 to 100 we have made. Then CPU from 250 to 300. Let's do it to 300. Then also for the limits, let's increase this from 128 to 150. Then from 500 to 600. Save. And now let's increase the replica count from 1 to 2. So we have made all the changes to increase the resources such as memory, CPU, and also have increased the replicas. So now we will have 2 replicas for the post service which will run to handle the extra load. Now let's save this file, and now let's update this file to the CloudShell so that we can deploy the updated file. Let's upload post depl. It is the post depl. File successfully uploaded. Now let's qct apply f, then post table, apply it, configured, service unchanged. Now let's check the status. eksctl get pods. Oh, there's invalid image name. Oh, we need to provide the image name because it was dynamically generated during the CI/CD pipeline. Let's quickly update the image name here. Docker Hub CI pipeline has pushed the image, built image, to the Docker Hub. We'll collect that image with the proper tag name. This for post service. We'll collect the recent image name from there with the proper tag and then paste that. This is the recent one. Let's collect this, copy this, and then come in here. Then we'll be pasting this in here. Let's make it 2 copies. Let's connect this and then copy this, and then until here we will paste this one. Now let's quickly upload this file in the CloudShell. Let's first delete the previous one, rf post MongoDB. It is removed. Now let's upload the new one, new updated one. PostDevel file successfully uploaded. Now let's apply eksctl apply PostDevel YAML. It's successfully configured. Now let's check the pod status. eksctl get pods. We can see the PostDevel is now running fine without any issue. So the pod is running with the increased resources, here, with the increased resources, and there should be 2 replicas. We can see there is PostDevel, this is 1, which is running fine 8 seconds ago, and the PostDevel, this is also running fine, 1 by 1 running fine 9 seconds ago. So there is 2 replicas which we can see. So we have increased the resources and also the replicas to handle the extra load on the post service. So this way we can scale the application, which will provide us a reliable application by handling the extra load. Now let's take another example to validate the reliability of our microservice application. In our previous example, we said that there can be extra load on the application, and one service like the post service or any other service out there can be in trouble for the extra load. Now, as the microservices are built with independent small functioning applications, here we can see the pods are representing the independent functioning applications. So this service down won't make any impact to the other services. Let's see with our pods. Let's get the pods again. eksctl get pods. So here all the pods are running fine without any issue currently. You can see. Now to down any one service, let's choose this command service, the first one. We'll delete the deployment of it, and for that let's get the deployments. eksctl get deployments and see what is the deployment name. Command depl. Now let's delete eksctl delete deployment. Then we'll copy the deployment name and then paste it on here, and let's hit enter. So we have deleted, we can see deployment apps command depl deleted. So we have deleted the deployment of the command service successfully. Now let's check all the pods status. eksctl get pods. See, the pod comment DEPL, which was there, but now comment DEPL is not there. From comment Mongo it starts. So the pod for the comment service is not there, so it's not functioning. But all the other pods, we can see all the other pods are running fine without any issue. And from this we can say that the microservice application which we do have is reliable. Now let's take another example to validate the reliability of our microservice based application. Imagine we want to scale our app by updating the front end and adding more backend services to enhance its functionality. To achieve this, we would need a team working on different components. Since microservices are independent, team members can work on various services simultaneously without dependencies or bottlenecks. This accelerates the development process, allowing us to update and deliver the application much faster. And this rapid development and deployment cycle not only enhances efficiency but also reinforces the reliability of the microservice architecture. So this was all about the reliability of our microservice application, and for achieving this reliability we deployed our microservice application to the Kubernetes cluster in the cloud. Now we will talk about the lacking with scaling which we do have with our app, and we'll also talk how the app can be useful having this lacking. So here we have manually scaled our microservices by modifying the Kubernetes configuration files previously, as we did for the post service. However, microservices are typically designed for elastic or automatic scaling, allowing them to adjust dynamically based on traffic demand. While auto scaling is ideal, some applications can still benefit from manual scaling in specific environments. For instance, if a microservice is deployed on premise or in a resource limited environment such as a dedicated data center with a fixed number of servers, auto scaling may not be an option here. In such cases, scaling is done manually based on historical trends, as seen in government or banking systems where infrastructure is provisioned manually. And another example is applications with stable traffic patterns. If an app doesn't experience frequent traffic spikes, keeping a fixed number of instances running may be sufficient. This is common for portfolio websites or small business e-commerce apps with steady daily users. So manual scaling allows for a predictable infrastructure cost while maintaining reliability. When needed, auto scaling can be implemented, and microservice architecture always keeps the door open for future scalability. This flexibility makes microservices valuable even in environments where manual scaling is preferred. And this way, the microservice application we built for creating posts and comments can effectively operate with manual scaling while remaining adaptable for future scalability. Now let's wrap up our discussion on microservices. So far we have deployed our microservices on the cloud using CI/CD pipeline and explored related cloud resources and their communication from console home instead of the AWS cloud, using necessary architecture diagrams for the infrastructure resources, for the application resources instead of the Kubernetes cluster. So explored related cloud resources and their communication and examined how our application interacts both internally and externally. We also covered the benefits of our microservice application along with the challenges of scaling. With that done, it's time to delete the AWS resources we created to avoid unnecessary cost, as they were only set up for demonstrating and testing purposes. So it's time to delete the resources. So let's go for that. Now, to delete the resources, we'll be following this text file, which can be found inside of our project's root directory under of task before after CI/CD folder. So we can follow from this point here, deleting the resources created so far. From here, we can follow the guide and delete the resources which have been created so far in the AWS cloud. So for deleting the resources, maintain the deleting order here from order list from top to bottom as specified here in the text file. So let's start deleting using the AWS CLI commands CloudShell from the AWS Cloud Console. First, we will delete the uploaded files in the CloudShell, and for that, let's go to the CloudShell. Let's clear the terminal. Now let's list the files which have been uploaded here. Let's type rmrf. It will delete the files recursively. Let's put the files one by one. Let's delete like this way. Then rm, let's list again. These are there. rmrf, then so we can see all the files are deleted from here, uploaded files. Now there's no file. Now before we delete the Kubernetes cluster, we'll be deleting the node groups. To delete the node groups, let's list the node groups first and then delete. It will list the node groups. This is the node group name. Let's copy this command and we'll have to modify this here. Node group, we'll have to provide the node group name from here, which is primary, and then the numbers. Let's modify it, or maybe we can run this command. Let's run it because we have tagged before. Let's run this, see if it works or not. No, we'll have to modify. So node groups, let's copy the node groups name from here. Now let's modify the command. Now let's run. Clear. So let's wait until the node groups delete, and after that we'll be able to delete the Kubernetes cluster. We will check the status from here, deleting status for the node groups from here, and for that we will check if the node groups is still there or not. It is still there. Let's wait until it delete. Let's check the status again. It is still there. Let's wait. Let's check the status again. Node groups is still there. Let's check the status again. Still there. So we have successfully deleted the node groups. You can see the node groups, there's an empty array for the node groups. So we have deleted the node groups. Now it's time for the Kubernetes cluster, Elastic Kubernetes cluster. So we will delete this from the Cloud Console, AWS Management Console, and by deleting the Kubernetes cluster, we will delete all the Kubernetes resources, which means our app resources. So let's go for that. We will go to Elastic Kubernetes Service. Then from here we'll select the cluster, which is MERN micro app cluster. This is our app cluster name. It is active currently. Now let's delete this one. Delete. To confirm the deletion, we'll have to type the name here, then delete. Deleting. Status is deleting, so let's wait until it finishes the deleting. Oh, we have successfully deleted our Kubernetes cluster. Nice. Now let's go for the load balancer and key pairs from the EC2 dashboard. Let's go to the EC2 dashboard from the console home, EC2. We have landed on the dashboard. Now let's delete load balancers and key pairs. First load balancers, where this one. Select all. Now let's go to actions, then delete load balancer, then type confirm. Successfully deleted the load balancers. So we have done with the load balancers. Now it's time for key pairs. There is key pairs. Let's select the key pair, then go to actions, then delete, and could associate with one more instances, type delete. To confirm deletion, type delete. Delete. So successfully deleted one key pairs. Now it's time to delete the VPCs and the DHCP option sets. Let's delete the VPC. Yeah, we'll have to go to VPC dashboard. Let's close it. Then where's VPC? Here's VPC. We have landed on the dashboard. Now navigate to the VPCs. Now select VPC. Now go to actions. Now delete VPC. So to confirm deletion, type delete. It is showing what other resources will be deleted. We can see internet gateway, security groups. So those are also listed here. So let's delete. Deleting is on process. So we have successfully deleted our VPC. Let's see and refresh the resources. Let's see what else there. DHCP option sets is there, and everything else is deleted. So DHCP option sets, select actions, delete DHCP option set. To confirm, type delete, copied it, pasted, delete DHCP option set. So we have successfully deleted the DHCP option set. Now EC2 instances launch template. Now let's go to EC2 instances. Let's again go to EC2. Let's see is anything is remaining in here. Instances are in terminated state, so this will be deleted after some moments. Now for launch templates, under instances we'll have launch templates. Select it. Now go to actions, delete template. Delete template. Confirm, type delete. So we have successfully deleted the launch template. Now what else remains? DynamoDB tables. Let's go to, from here, DynamoDB service, then go to tables. Here's our table. Let's select this, then delete, confirm, delete. So we have deleted the Terraform state log table. Then Amazon S3 general purpose buckets. Let's go for that. Amazon S3. Here's S3. Then general purpose buckets, then select the bucket, first empty it, then delete. Let's see what happens when we click delete. The bucket is not empty. It will ask to empty the bucket first and then delete. So let's first empty the bucket. So let's permanently delete all the objects inside of the bucket, and to do that we'll have to type permanently delete and then delete the objects inside of the bucket, and for that empty. So the bucket is now empty. Now we can delete it, and to do that we'll have to exit from here. Now select the bucket, now delete. Now to confirm the deletion, enter the name of the bucket. Let's copy the name and paste it on here. Now delete bucket. So we have successfully deleted the bucket from Amazon S3. Then what else remains? AWS certificate manager. So let's go for that. To delete the certificate manager. Here we can see list certificates. Here's our certificate. Select that, then delete. To confirm the deletion, type delete, then delete. So we have successfully deleted our certificate also. Now delete KMS alias encryption keys. Okay, to delete that, AWS KMS list aliases query. Yes, let's list the KMS alias first. Let's clear the terminal here. Open a new terminal. Then list the KMS alias. Okay, the alias is there. Now let's delete the KMS alias. We can see alias name, alias KMS MERN micro app cluster. We have listed all the KMS alias which is inside of this name of our cluster. So let's delete all of these aliases. Let's list again, see those are still there or not. So we can see an empty array now. So we have successfully deleted the KMS aliases. Then delete EKS CloudWatch logs. Okay, let's see what are the logs we have for MERN micro app cluster. Let's list the log groups. Yeah, these are the log groups. Now to delete that, this is the name, so we don't have to modify anything. We'll have to just paste the delete command and then enter. We have deleted. Let's check still the group is there or not. So there's no log groups. We can see an empty array. So the log groups has been deleted. Now it's time for IAM roles, policies, and the identity providers. Now let's go to IAM from the console home. IAM, then first roles for, let's go to 8 roles, and from there can we, no, we'll have to delete one by one. Okay, Amazon service role, let's delete this one. Let's copy quickly and then delete. Deletion in progress. Let's delete this one and then copy. Deleted. Then for this one, role name, then delete. Now delete this one. And for these two roles, AWS service role for support and AWS service role for trusted advisor, these two roles we can see here. Last activity, there's no last activity, but here which are recently created for our app by our CI/CD pipeline run, we can see here the last activity is showing on these roles but not these two, because these two has been created from our root user account. AWS service role for support, probably these two created when we contacted for the or applied for the AWS support. So we cannot delete these two roles. To delete these roles, we'll have to go to the root user account and then delete. So we don't need to delete these two right now. Let's delete these two. Can we? Yeah. Confirm, delete. Let's type delete. So all the roles which were there created for our app are now deleted. Now we can move forward for deleting the policies. Let's go for that. Here, let's refresh. You can see 8 roles were there. Now we can see 2 which we can't delete. Now policies. Delete. Let's delete one by one. Delete. Confirm the deletion. There. So the policies are deleted which has been created for our app. Now this administrator access and which one? Billing access. These 2 policies are attached to our IAM user account. We don't need to delete these 2. To delete these 2, we will have to go to the root user account, and actually we don't need to delete these 2 because these are for the IAM user scope. So let's go for deleting the identity providers. Refresh. No policies. Now identity providers. Let's select delete. To confirm removal, type confirm. Delete. So the identity provider has been deleted. Let's see. So we have deleted the IAM resources which were there for our application. So we have done deleting all the resources which were there for our application. Now it's time for making a conclusion. Now let's make a conclusion here. Since the entire process from the deployment to deletion can be quite lengthy, the attached text files here, these 2 attached text files in the project's root directory is referred to speed things up. Now before we wrap up, let's take a quick look at what's coming next. We'll be diving into the Google Cloud Platform, GCP, one of today's leading cloud providers, to deploy a more advanced microservice project. And this new project will address the limitations we encountered in our previous microservice application. Throughout that project, we identified several key challenges, particularly in areas critical to the DevOps lifecycle. These limitations affected automation, security, scalability, and monitoring. Let's have a brief discussion about them. The first one is infrastructure management. For this, we saw that the application lacked automatic scaling and deployment automation, and for which we had to manually scale services, and also we had to deploy Ingress by running multiple commands. And then additionally, the deployment wasn't fully cloud native, as we had to rely on Docker Hub to store and pull Docker images instead of using a cloud integrated container registry. And then the second one is security and compliance. We saw that with our previous deployment, the Kubernetes cluster was public, which is fine for non-sensitive applications, but there could be a security risk if sensitive data were involved. A private cluster would be a more secure solution here. And then we authenticated to AWS using hard-coded access keys stored as GitLab-ci.yd variables, which increases security risk. A more secure approach would be to use OIDC-based workload identity federation, eliminating static credentials and reducing exposure. And then we used an IAM user with full admin access, which granted excessive permissions while automatically creating and deploying resources through the CI/CD pipeline. A more secure approach would be to use a least privilege impersonated service account or an equivalent mechanism restricting access to only the necessary roles. And then lastly, the Kubernetes configuration was missing the secrets. While our app didn't contain any sensitive information, the lack of proper authorization in the Mongo Express and RabbitMQ management UI allowed us to bypass the need for secrets. Therefore, we can conclude that the secrets were absent in the Kubernetes configuration. So this was the second one for security and compliance. And the third one is CI/CD pipeline. We saw that although we had automated builds and deployments, the pipeline lacked automated scanning for vulnerabilities and testing to catch issues before deployment. Then number 4 is monitoring and logging. We saw that there was no performance tracking, centralized logging, or monitoring dashboards to analyze application behavior and detect issues in real time. And then the last one is incident response. We saw that the system lacked an alerting mechanism, meaning there was no automated notifications for incidents or threshold breaches. So in our upcoming microservice project on GCP, we will try to overcome all of these issues by deploying a fully automated, DevOps-driven, secure microservice application. So let's meet there. Thank you.